Welcome to APEC. It is September 30th, and I am your moderator, Tim Ventura. I want to thank everybody for joining us on today's call, along with everybody watching us on YouTube. So today we have some really special presentations. Jeremy Rys is going to present a completely updated analysis of reverse engineered UAP technology. He's going to be run through metamaterials, the latest and the greatest. He has been working on this thing all week long, so I'm super excited. He's going to be starting things out. David Chester is going to run through a quantitative analogy between gravity and condensed matter. This is something he presented at the Sarfatti Cortona conference this summer. Again, very, very exciting new material. And then Jack Sarfatti hopefully will be able to join us to discuss UAP propulsion physics. Jack is dealing with some scheduling issues, so he may or may not be here. I have also sent out a couple of mystery invites, we'll call them. We'll see if anybody shows up later for that. We may have some pretty exciting guests pop on later in the conference. We're also going to be hearing updates from our lab partners, and we have a lot of that going on, especially like Mark Sokol at Falcon Space are doing amazing things. Brian St. Clair also told me that he wants to do some lab updates as well. So before we get started, today's event is on StreamYard. We are broadcasting through the Alt Propulsion YouTube channel. I absolutely love StreamYard. It is not perfect for everything, but for doing webinars like this, it is amazing. Big thank you to Bernie for setting us up with StreamYard. If you haven't subscribed to the Alt Propulsion channel, please do so now. You can ask questions using the live chat feature on the right-hand side of the page that you're actually watching this on YouTube. And we're going to try and ask them to our presenters depending on time constraints. Also, depending on what kind of time we have, I would like to later in the day kind of throw the doors open and get some other folks in StreamYard. So at some point, we may post a StreamYard link in chat for you. We're going to have conference replays, details, and speaker info on our website at altpropulsion.com. If you haven't registered there yet, please go there now, altpropulsion.com. Please sign up for our mailing list and tell a few friends about it. Help us grow, help us serve the entire community. I am promoting this on Twitter, Reddit, LinkedIn, Facebook groups, you name it. So all of those places, if you guys have channels on those, if you guys have friends, folks that you're connected with who are into this, let them know about APEC, get them signed up for that mailing list, and that way they will get reminders for these conferences. I also want to let you know that we have all of this on a calendar on the APEC website. So the open mic stuff is scheduled well in advance. I just finished getting the emails set up through the rest of the year. The live ones, we're trying to schedule those about a month or two out. And we also have placeholders so that you know what time they are. So without any further ado here, I want to introduce our first presenter who needs really no introduction. Mr. Jeremy Rys will present a completely updated analysis of reverse engineered UAP technology from its historical origins to current DoD investigation and congressional hearings, along with research suggestions on UAP reverse engineering for advanced propulsion applications. So Jeremy actually has done so much on this. He wanted to organize it. He has exactly a 1 hour long video he's going to be playing for us. And so I'm going to bring him on so that he can kick that off for us. I'm really excited. He started digging into this and he just kept pinging me. He's like, Tim, you have no idea how much new material is here and how rapidly this is changing. So again, I'm going to add Jeremy in here. Sir, welcome. Welcome to APEC. Thank you. Big thank you for joining us. And
yes.
You actually have a video, and that way you didn't want to miss anything. So if you can kick that off, and then we'll just kind of roll from there.
So here it is. It was pre-recorded. I did it once, and then I decided I wanted to change it all around and add more stuff and make it better.
Okay. And once you get going with it, I will take us out. We'll be invisible, and this will just play for the audience. And I will come back in at the end of it and then introduce Mr. David Chester. So
all right, we'll see. Hopefully the audio works. All right, guys. All right. My name is Jeremy Rys. I have a bachelor's degree in physics from Bridgewater State University, and I've been studying metamaterials since 2004. This is a presentation I put together on metamaterials for warp drive and advanced optical cloaking. I'm going to talk about metamaterials in nature. We're going to talk about the theory behind metamaterials and the practice of actually building them. And let's begin. So metamaterials are used for tons of different things in industry and commercial uses today: AI and data economy, electronics and photonics, healthcare, transport, communication, space, energy, sustainability, and all sorts of things in between. So there's a lot of production here, a lot of future, a lot of industries starting up. The intelligence agencies are interested in metamaterials. Kinetic is a British defense company, BAE Systems, and we can track some of the metamaterial scientists who have come from BAE to Kinetic to work on advanced metamaterials and these types of systems. Another person who went to go work at Kinetic was George Tenet, former CIA director. In 2006, he left the CIA and went to go work for this company. So it's obvious that a lot of people are really interested in this. And BAE scientist Sajjad Haq, go look him up on Google Scholar. You'll find some really interesting stuff on metamaterials and some of the research being done. And also look up his blogs on Kinetic as well. He has connections to the Queen of England, or had until she died, I guess. So he's definitely up there and something going on with the research that he's doing. Very well connected guy. Lots of fascinating stuff to look up there. One of the things they're working on is 3D printed nanomaterials, and this is I said this would be the future. 15, 20 years ago, when I was started making videos on metamaterials, trying to get people interested in this topic. And look, it turns out here we are in that future. Amazing what they're doing with the nano printing at the nanoscale these days. Now, George Palikaras is the president and CEO of Metamaterials Incorporated, called Meta also. And they specialize in smart materials and nanotechnology with the vision to bring the benefits of materials and nanotechnology to the world. This company's out of Nova Scotia. They're up in Dartmouth, Nova Scotia. Really interesting research they're doing. A lot of super lenses and other things we'll talk about here soon. If you're interested in studying metamaterials as a student, Duke University has an awesome program. So as does a couple of the universities like Rensselaer Polytech, Rochester, in New York. But Duke is probably one of the world's leading and top research places if you want to get a degree in metamaterials here in the U.S. Now, the history, how we discovered metamaterials and the materials of optical science in general, started with way back in history, actually, before any of these guys. Book 2 of his Republic, Plato tells the story of a ring which grants the power to become invisible at will. This is only, mythical, of course. Kind of start understanding where J.R.R. Tolkien got the idea from. I just read his Greek history. But through the ring, the sophist Glaucon discusses whether a typical person would be moral if they didn't ever have to face the consequences of their actions. So, yeah, you could go rob the bank vault, all kinds of cool things you could do with a ring that makes you invisible. If you had such a ring, what would you do with it? So that's an important question to ask oneself. And this is his, talking about the Republic and how sometimes we can be invisible and do things, and but is it really for the greater benefit of our fellow man? Not always, and it turns out that even things we do when we think we're invisible in this world eventually come to light. So all things do. There are animals in the animal kingdom that have figured out clever ways to become invisible, whether that's through making their tissues clear, jellyfish or some of these other types of fish that have completely clear bodies, um, to animals that know how to camouflage themselves or look like other things. Um, so really interesting way that nature does it. The most sophisticated camouflage in the animal kingdom is a metamaterial which consists of 3 layers, and each layer has muscles which can contract to make the layer appear or disappear, or let light through. And what these 3 layers do is remarkable in their ability to reflect certain frequencies of wavelengths of light and not others. And yeah, this is a chameleon, by the way. Fascinating creature. The blue it's turned into. So all right, let's next. The cuttlefish is probably the most sophisticated camouflage in the animal kingdom. I'm not going to play this video because it's a bit long, but it tries to copy this checkerboard pattern. Does a pretty good job. It can't quite get the intelligent patterns and stuff like that, but it's certainly pretty good at what it does. So based on the research that was done into how the chameleon skins do it, there's been research that's going on and ongoing into how to produce materials which you can change the color to adapt to fit any given environment. And so they're developing these layers which can effectively, and there's tons of more research on this, and probably better pictures and stuff than I have here, but they have the ability to change color under different conditions to match the environment. So then we have phased optical detectors. So phased array is scientists figured out with antennas that you can get a much stronger signal, both transmission and detection, if you use several antennas or several cameras or optical detectors instead of just one. And if you arrange these in an array and do the proper matrix mechanics on that array, you can get better, really high quality optical definition. And so the nature animal kingdom figured this out in the fly's eye, basically by knowing that one detector wasn't enough, and it just made a ton of them rather than evolving a more sophisticated eye. Like a human eye is much more advanced and sophisticated than the fly's eye. But if you're only working with what you got, guess you can come up with some pretty ingenious things. Chitin and the metamaterial is a metamaterial of the insect world. So with chitin, it's fascinating what we've learned about the structure of materials on the nanoscale and how that can affect things on the macroscopic scale, because you can make regular organic, beetle wing material look like metal, shiny gold metal, and you can make metals look transparent, and with aluminum oxynitrate or ALON, transparent aluminum glass. And this was interesting because it was theorized in the Star Trek before it was a real thing. So Star Trek actually predicted this and said, "Oh, what about transparent aluminum?" There's a whole episode on it. Trekkie fans are familiar with it, and then it now is a real thing. So it's weird case of Star Trek actually predicting the future, and they got the element right too, which is even more amazing. But yeah, it's interesting the ability of these materials on the nanoscale to affect light in such a way that you can make things that are metallic look non-metallic and things that are metallic look not metallic, and vice versa. So crystals and crystal growth. Crystals are a metamaterial. They're a whole bunch of individual cells that are all aligned in the structure gives it its optical properties, its ability to be clear. The structure of the crystal mediates how the light is able to pass through it, because it's a coherent phase transition from one side of the crystal to the other without diffraction or bending of the light. It has a clear exciton path through the crystal, which we'll talk about in a second. Now it's interesting that water freezes differently than, say, other crystals grow. Other crystals have different shapes, and some crystals have really strange shapes. The crystal structure and the shape that a crystal makes is based on its outer electron orbits, or its physical chemistry. Ice, of course, has a hexagonal structure, whereas table salt has a cubic or grid-like structure. And that's evident in their macroscopic evolution of the crystal. The crystal structure matches the atomic structure of how it grows, because it's all built on atomic building blocks which stack, and it's all based on electron configuration. Of course, the outer electron shells in atoms, this Lewis structure, and the covalent bonds of the electrons are what form at these points in the junctions of the crystal. So you can make some pretty elaborate crystals and some pretty elaborate structures based on what you can do with the unit cells there at the macroscopic level. But it turns out all three of these can be clear, and all three of them can be metamaterial. So again, it's not just purely the structure of these things that make it a metamaterial, although when you arrange other things like in these structures, you get metamaterials. But the things you have to arrange in those structures are generally dielectrics. They have dielectric properties. So what is a dielectric? The electromagnetic spectrum, of course, interacts with all these things in different wavelengths. But when things are dielectrics, they have different interactions with light. So there's ionizing radiation and non-ionizing radiation. The ionizing radiation pretty much goes through everything, but when it hits something, it has so much energy, it usually knocks it loose. So it's dangerous in that regard. Whereas non-ionizing radiation can still be dangerous. You can still get a sunburn. You can still get, these waves that can cause adverse biological effects potentially. But as far as penetration goes into a substance, it's all based on those electron shells and this and Snell's law, the index of refraction. So when things have a different index of refraction, light hits one object. When light's going through one medium, it's fine. As soon as it hits another medium, it has to change paths, and it slows down, and that causes refraction or reflection or transmission or both, or total absorption. There's a couple different things that can happen in an interaction with light and matter. But the coolest thing that can happen is if you have things if you can match the refractive index of the medium. So if you could match the refractive index of air, for example, you could potentially make things invisible. And this is shown by pouring this fluid into these beakers. So these beakers have a refractive index of glass, and this oil that he's pouring into the beakers has the same refractive index as the glass. And when you have that fluid where the refractive indexes match, it creates this invisibility effect. So if you were to basically create a shell that had the same refractive index as air, it could reflect light. Or if you could create a metamaterial with a negative refractive index, it would have a lower refractive index, and it could bend the light around it completely. I wish that was shown with materials that have a lower refractive index, so you can make an invisibility cloak out of that. Now, turns out this is crystal here, and this is regular soda lime glass, and the difference in the impurities is based on this dielectric permittivity, and the electrical structure of the glass. So if you want the best glass and the clearest glass, you'd have to have a perfect dielectric, a totally lossless medium. And if you want a perfect conductor, like a superconductor, you have to have the opposite of that's the opposite of a dielectric. So in a superconductor, the electrons are all so free and shared everywhere completely over the entire structure of the superconductor that the electrons are just free to go. So you get superconductivity, that all points are equal on the surface of that superconductor, and you get total magnetic field expulsion. In a perfect dielectric, what you have is the opposite. The electrons are bound super tightly to the atoms and to the nuclei, so that any kind of disturbance that pushes the electron away instantly bounces it back. And those are really great for sending waves through, it turns out, because they're so bouncy. So the higher the dielectric, the higher the electrical permittivity, and I mean the lower the electrical permittivity here, and thus the higher the it's a perfect dielectric. It's a lossless medium. You don't get any losses. Whereas if you have a perfect conductor, or even metals, when you try to shine light on a metal, it only interacts with the surface. It can't penetrate the material and form an exciton, or these quasi particles that travel through the material. It doesn't do that, and instead it creates what's called a surface plasmon, a quasi particle on the surface, and it either bounces off the surface or diffracts into the surface of the material. And so those are the quasi particles, and how they kind of work with the interaction of materials with the electromagnetic field. And it's interesting how optics works in these cases. There are some materials which are really good at diffraction, and some that are really good at scattering, and some that are really good at absorption. And we'll talk about some of those materials here and why they work that way. Now, glass and fiber optics, plastics and stuff, these clear plastics and clear glass filaments, they work really good for signals, to send signals long distance without any loss, because of something called total internal reflection. Turns out that once you have light past a critical angle, like if you go underwater and try to look at the surface of the water past a critical angle, it turns into this total internal reflection, where you see that completely reflected. And you can see this inside of a fish tank. If you try to look through the fish tank and look from the fish's point of view through the surface of the fish tank, it won't work because of total internal reflection. And that's what allows fiber optics to work inside of these fiber optic cables, because the signals constantly bounce back and forth on the walls and travels along the cable, and it won't ever leave that medium because of that critical angle. And now the same thing works inside of the mirage effect, or fata morgana, where a phenomenon where ships look like they're floating out at sea. This is caused by the refractive index being significantly different in two bodies of air that touch each other. So you have a hot body of air and a cold body of air, and it acts as almost like it's bouncing off glass or the surface of the water because of that angle. Again, it's past that critical angle here that we talked about before with total internal reflection, and that medium of the refractive index difference of that hot air body on the top of the cool air causes this optical effect. And we can observe that here with these carbon nanotube sheets. When they run the electricity through this carbon nanotubes, they heat up really hot and create that refractive index change along the surface of the water. The water is a much hotter temperature there, and the refractive index is such that you get total internal reflection at this angle. So what you're seeing is actually the wall behind reflected off of this. It's not actually turning it completely invisible. It's kind of not real. It's not real concealment. In any case, Brewster's angle is another one. Is the opposite. Brewster's angle is where you get total transmission, and it's the optical angle of attack for if you want all of your laser or all of your light wave to go into a material. Brewster's angle is turns out to be the one for that. And it's 57 degrees, kind of a strange angle, but it's there. Negative refractive index was first theorized by Victor Veselago, and in a negative refractive index material, light travels through that material faster than it would travel through the empty space there. But it can't violate the speed of light itself. So what happens is the phase velocity actually goes this faster than the speed of light, while the group velocity still obeys the speed of light. So you don't get Einstein violations in these materials, but you can still get faster than light transmission through them at the phase velocity. That can be explained more. I have another lecture on here. So anyone who wants more information on this can go back over the slides and look into this more. Now, we talked about electrical permittivity. Now, the magnetic analog is magnetic permeability. It's how much magnetic field will penetrate inside of an object and actually be permeated inside the material. So a superconductor expels the magnetic field entirely. So it's a superconductor. You'd have a mu of either infinity or zero. It's zero probably, because the permittivity would be nothing. But quasi-particles are the next thing, because you have this magnetic effect, and you have to understand that particles themselves are like magnets, and they have resonance, which we'll get into in a second. But the quasi-particles exist as these excitons, or you have all these electrons that are tightly bounded, so that when an external electromagnetic field comes into the crystal or the lattice, it's easily propagated through the lattice because the particles are so tightly bound with their neighbors. It's like there's coupling in the springs of this. So a couple different modes that can happen with these the coupling that exists and the vibrations of the lattice structure. There's actually 6 of them that can be identified as vibrational modes in a lattice structure. And those vibrational modes correspond also to harmonics and quantum harmonics and the oscillations. So, for every mode you have multiple harmonics of that mode. And it's important to understand those phonon modes, the vibrational modes of your lattice, which ones exist in your particular lattice and which ones are damped. And then be able to vibrate your lattice accordingly to get the necessary effect that you want. Now, phonons, these lattice vibrations, are caused by the like spring or magnetic interaction. Again, these are dielectrics, so they're tightly bound, and that property of the materials is what essentially leads to the ability for glass and other materials to be clear and crystals to become clear. Now, the orbits are themselves a little tricky business, but basically the atoms are resonators, and they have these orbitals that are predictable with probabilities. And these probability functions and orbitals are essentially clouds of resonance, and they have wavelengths and frequencies. And nuclear magnetic resonance is, of course, people know NMR. It's just called an MRI machine because they took the nuclear out, because people would be afraid to get in it if it was called a nuclear magnetic resonance imager rather than a magnetic resonance imaging. So they're fine to get in a magnet, but when they figure out that it's actually doing nuclear stuff, they get freaked out because they don't understand it. But in reality, nuclear is just nucleus of the atom, and the nucleus of our atom are protons, and protons can be talked to using a certain frequency of their resonance frequency. So it turns out when you put protons in an electromagnetic field, hydrogen atoms, in this electrostatic field, a magnetic field. Sorry, you get it in a magnetic field, and they line up according to the magnetic field to their spins. And then you pump an opposite magnetic field, and you measure the time dilation of how it relaxes. Now, whatever's around it, it's going to cause it to change a little bit differently, or have a little bit different frequency, because it's going to be interacting with all the different stuff that's around it. And those interactions are what you want to read. Those contain information about your sample. So, for example, in chemistry, NMR is used for spectroscopy. And the way they do it is they take a sample of what you want to find out, whatever it is, and you put it in some water. And when you dissolve it in the water, you put it in the NMR machine. It spins it up and down with the magnets and measures the relaxation of the Larmor precession as the thing realigns to the new magnetic field as the magnetic field spins. Now, in this thing, it's a magnet that spins around and spins around and around and around, and it looks like a Stargate, but it's collecting three-dimensional image information from all sides, and the fields are constantly flipping back and forth. And it's a very, very strong magnet. You can't get any metal or anything near this, close to it. Not a good thing. But it all works the same. There's a magnetic field. It splits. It spins it one way and then spins it the other, and then it measures the detector signal of what the protons are doing, and that signal gives peaks of the resonances of whatever the frequencies of whatever's around it. So if it's got iron here, it's going to have a peak from iron, and if it's got cobalt over here, or nickel or brass, we're going to be able to tell what's around atomically on the structure, and be able to say, okay, well, that we got tin and copper here, so it looks like we got brass, or we got titanium alloy here. So you'll be able to tell carbon and steel. Okay, is there manganese? Okay, well, we got this must be structural steel because it's got carbon and manganese in it. Versus, this is an iron magnet. So you can tell like a lot about materials based on talking to their protons, and this concept of nuclear magnetic resonance, which won the Nobel Prize for nuclear magnetic resonance for Edward Mills Purcell, who was one of the scientists that the CIA hired to run Project Rainbow. They wanted to map the entire electromagnetic spectrum and understand all the EMF, or electromagnetic feedback response, that they got from any material. With you hit it with frequency, what's the response? They wanted to map out all the different materials, all the different responses, and come up with. They came up with the whole idea for the FCC's list of table of frequencies. So all the frequency allocation tables, which allocate which frequencies can be used and can't, and are reserved for military and whatnot. And they started identifying the bad frequencies that can be used for different things, and all that. Now, they weren't the first ones to be working on invisibility and metamaterials. First metamaterials that were used for military that I'm aware of was the German anechoic tiles of 1940 and 41. This project was codenamed Alberic, after the invisible guardian dwarf of German legend. Now, U-480 was a stealth sub. There are several other ones. If you look up U-480, you can find a whole list of all the stealth subs that were outfitted with these anechoic tiles in the Nazi fleet. And one of them actually, was involved in this big fight and sat at the bottom of the English Channel for a couple weeks to try to avoid detection, and they were fine. It sunk a whole bunch of ships and was causing all this problems in the English Channel. And then they eventually got it by they evacuated all the boats out of the channel and set up minefields on both ends of the channel, and it was trying to get out and hit one of the mines, I think, and got taken out. But anyways, it's undoubted that we got a lot of this intelligence from guys like Dornberger and other Operation Paperclip scientists that were brought from the Nazi Germany over to Huntsville, Alabama, and mainly Huntsville, Alabama, to engage in intelligence collection from whatever we could get from the Nazis. And of course, we took this knowledge and we're using it to develop invisibility cloaks for our U-2 project during the 1950s in the Cold War. This wallpaper stuff turned out to be too heavy and bulky and messed up the flight characteristics of the plane too much to be of any practical use. But some of it was recovered on National Geographic by a guy named Peter Merlin, who recovers a lot of stuff from crashed sites. He goes to the X-planes and crash sites and recovers a lot of those things. So definitely go check that out in his work if you can, Peter Merlin. Now, HARP is an example, and the woodpecker, the Russian woodpecker, these over-the-horizon radar systems and systems designed to interrupt over-the-horizon radar by creating ionic spheric storms and resonances in the ionosphere. These technologies are phased array. So, and they're metamaterials. So they have all these antenna systems in these field, and they're arranged in a grid-like pattern. This is a metamaterial. It's a meta antenna, and it's phased array. So phased array antenna systems. This is a 1958 image of a solid-state phased array radar system from courtesy of DARPA's website, and you can see the height of this compared to the pickup truck, and all these are little detectors that are mapped out in this octagon here, and the phased array of this they can use to pick up more signals. So the antenna is basically if they develop the phase or the timing between these pulses, they can get them to activate at different times, which can cause, it's called beam steering or angling of the beam through a phased array. So they're much better detectors, much better transmitters. So definitely check out phased array. This is another phased array optical antenna device. These are all emitters in a grid-like pattern. The ability of this to detect high quality, high definition signal. So in typical radar, you don't get the signal quality or the definition of whatever you're recording or looking at like you do with phased array. So phased array systems, they're in Antarctica, they're in our poles, they're in, they're all over, and they work on a matrix. There's all kinds of matrices and deep math and physics stuff on how phased array controllers should work. Here's just a visual graphic demonstration of a one-dimensional phased array system. So a linear phased array where they can basically do beam steering or control of the beam by changing the phases of which these emitters will hit at what times. And there's a whole science to it. Again, not the place or the time to look into it, but definitely Defense Department applications. They had a $7.5 million MURI grant just to his work, this guy, Professor Anthony Gribik's work on developing metamaterials for a new generation of integrated electromagnetic and photonic systems. So lots of money, lots of research going on into this. There's also the application of metamaterials into camera systems and detectors as well. So these are all iPhone cameras taken out of an iPhone 11 or the next generation iPhone camera. They're all put in this special array, which has been machined to this specific standards and whatnot. And all these are then hooked up to a computer where they can get basically they form a 50 terabyte or 50 gigapixel image, a 50 gigapixel image from adding up all these cameras. And this is the Aware 2 camera from Duke University at the Pratt School of Engineering. But I know that the military has another version of this called the Argus 2, and that came out, a decade or two ago. I've played that before on some other videos, but yeah, the Argus, and that can actually, can zoom in and it can take an entire, I think, like 12 city blocks and just keep them under like surveillance, every square foot under constant surveillance they have these things on blimps and stuff. Really interesting technology. But metamaterials, MIT, of course, and Duke, they did these printable resonators. The first invisibility cloak, however, was actually built by a guy. The first invisibility cloaks were built by like John Pendry and those other teams and stuff. But the first person to actually be cloaked at microwave frequencies was this guy right here, an 18-year-old named Matt. But I met the guy who did this up at MIT in 2011 at a cold fusion conference. And he runs a company called Fractal Antenna Systems, fractantenna.com. And these are fractal metamaterials. So they're antennas that are shaped like in fractal patterns. And the metamaterial shape of the antenna actually increases the EMF resonance and the response by factors of significant factors that they're getting in the ability of these things as detectors. So he builds these little Koch snowflake antenna systems that you can put on your cell phone that will help your cell phone pick up better. And he's developed all kinds of stuff for the military, I believe too. He's got some other contracts going on with some of the fractal antenna research that he does. But it's cool that they built one and actually cloaked a person. So they're the first people to actually cloak a person. Only that it's at a specific microwave frequency. But it's still cool. So this quantum stealth is this light bending material you can look up. It's kind of like an invisibility cloak. It's basically an optical material that takes any light that hits it and stretches it out and skews it and blurs it. So it takes the majority of what's in the background and passes that through, and it will blur and obscure any kind of little thing that's not outside. So see how his shirt's starting to make up and his arm and stuff are making up too much of the picture, where his head's far enough away that it's kind of pushed over to the side here. You can kind of see his face, and his head is moved over to the side here and then stretched out really wide across the rest of the image. So it's interesting the way this material does to optics. There's also the green screen hoax it's a Harry Potter cape, but it's really a green screen that you use a still background and chroma key to remove green screen yourself invisible. Not a real invisibility cloak, but still looks cool on camera if you want to fake it. The nanotech chameleon skin suits. This is a technology of it's a projector. There's a camera, behind on his back, and it records what's behind him, and then it projects it onto the front. And it's not very invisible, to say the least. But it's cool. Some crude attempts, anyways. Yeah, these early types of resonators. There's tons more now. People have figured out way different ways to make resonators than just the C-ring types. There's so many more being built and 3D printed, and they got circuit board printers and tons of universities working on this stuff, doing cool stuff. So we talked about, John Pendry was the first person to coin the term metamaterial, I think in the early 90s when his group was working on some of the stuff. And but Victor Veselago was the first to theorize them with he did a paper on negative refractive indexes back in, I think, the 70s. So interesting history on these things anyway. 2000, the C-ring, split ring, and the Swiss roll, these were resonators that were built that some of the first invisibility cloaks and metamaterials. And again, it's based on the idea of, you have atoms in a crystal lattice are these nuclear magnetic resonators. And if you build these resonators that work for the electromagnetic field, they're basically like macro atoms, or large scale atoms, quasi particles. Essentially, they're a system of ring resonators that act like the same way that a metamaterial would on an atomic resonator would. There's also acoustic metamaterials for sound dampening and soundproofing. The U.S. Navy is working on a sonar invisibility project for submarines, and it's based on a lot of this research of, that the structure of materials can absorb sound. They can be optimized to for sound dampening or sound absorption, and a number of interesting scientists working on this currently. There's actually a Echo Noise Control Technologies Center in Ontario, Canada, that has the world's quietest room, and it uses acoustic metamaterials to dampen the sound. And a lot of research is done there into super sensitive microphones and other things that are super sensitive to mechanical vibration that need the sound to be completely, removed and eliminated from an environment. So yeah, this is crazy stuff, but it's metamaterials. And there's also acoustic chiral metamaterial inside your ear. It's the cochlea. You ever listen to a inside of a shell, and you can hear all the airwaves, and it sounds like the beach. It's like amplified through the structure of the inside of the shell. Well, that chiral metamaterial is actually responsible for amplifying the sound and noise signals inside your inner ear, so that they can be picked up by the cilia, or little tiny hairs that are on the inside of the cochlea. So as those hairs vibrate, they stimulate nervous systems. And the way it works is that actually the lower frequencies are in this part of the ear, and the higher frequencies are in the inner part of the spiral. So this actually works as a band gap filter to filter off all the different frequencies, so that the hairs here are hearing the lower frequencies, and the hairs inside here are hearing the higher frequencies, and such, so that all those hairs work together on different nerve patterns and different signals, to be able to say, oh, well, this is this note, or this is that note, or this, and those combine to create your auditory hearing structures of what you hear inside your head. Fascinating, the way it works, like a band gap. There's also a lot of research into chiral metamaterials. Check out Ron Kita's ChiralX group. He's got some interesting research going on into chiral metamaterials and their use in, these sinusoidally polarized waves, also called spatiotemporal optical vortices, or STOVs. Very interesting realm of research right now. Now, these are carbon nanotubes, and this is Vantablack. Now, the forest of carbon nanotubes provides this environment which is the opposite of a mirror. So a mirror is optimized for reflection. So any incident light waves on the surface will bounce right off. Light waves that touch this surface find themselves lost inside of a forest of tall really long carbon nanotubes. And that overall structure on the macro scale causes it to be one of the blackest materials ever created. It's deep, dark black, super black. Now, super cool to look at and stuff, but unfortunately, you start peeling that off and scraping it and scratching it, and getting those fibers up into the air and into your lungs, it can cause some problems. A number of people who worked on this technology and stuff have sadly and silently had to deal with the adverse health benefits of their classified work. One of them is the Fred Dunham story, and barium titanate in a similar type of material that is ferroelectric, that's very radar absorbent paint that they would paint the stealth fighter with. And they would have to, it's not very susceptible to the elements and the weather conditions, so they would have to scrape off and repaint these things very frequently. And it was apparently a very hazardous occupation. And then they took all the stuff that they scraped off, all this barium titanate and strontium and all this nasty stuff, and they put it in these burn pits and burned them. And the town complained. There was lawsuits that were filed. A bunch of people got really sick. A bunch of cattle died and sheep died. And there's a big story about that. But it's the downside of, you're working on this classified material. You don't want anyone to get a hold of it or find out about it, so you try to get rid of it, and you end up with a bunch of lawsuits and a bunch of sick people that you hurt. Well, active camouflage, again, is another area of research, has been for a while. 20 years ago, they were starting to develop a lot of this tech, way back in the day. There's a video 10 years ago from BAE with their stealth tanks, and I've posted, and I'll share in the links in the description of this below. There'll be a link to this presentation, and if you go through the slides and the speaker notes, there'll be links to all the slides for sources for more additional research. The adaptive camouflage system also works with a chroma key, a chromatic color changing thing, as well as an infrared panels that change the heat signature in infrared. So in infrared, a detector might look at these, series of chromatic panels, which can then be adjusted so that these ones are cool and these ones are slightly hotter, so that the profile of the real profile of the tank that's sitting there on thermal imaging will just look like a harmless SUV or family station wagon. So very cool technology. Again, there's ways around all this stealth technology using what's called quantum illumination and quantum radar. This is a Chinese quantum radar system, phased array quantum radar. And the idea behind quantum radar is that you take a pair of entangled photons from your source, you put them through a beam splitter, and you split those photons, and you keep one inside your internal clock, and you send one out to your target. And so that way, when your target beam comes back, you check it with the one that you saved from before to make sure that it's still entangled. Because if it's no longer entangled, that means you might have gotten spoofed somewhere in here, or that might, any kind of interaction that this has will break the entanglement through quantum interference, and therefore break your entanglement. Of course, the US has had a lot of problems with this. Apparently, it's revealed a lot of false positives, which kind of made them throw it away or abandon it. But the Chinese are still all about it, and they're still using it for some reason. And it makes me wonder if there's some other explanation for the false positives that we're seeing flying around. There might be just invisible stuff out there. Invisibility theory. If you're interested in more, mathematical theories on mappings and conformal gauge geometries and that kind of stuff, go check out all these papers here. There's a whole list of papers here for people who want to do further research. Now, metamaterials for construction and design, there's a whole nother type of metamaterials that we can talk about. Structural materials that are bendable and formable and actually functionable as machines. So this group doesn't consider metamaterials as materials, but they consider metamaterials as mechanical building blocks for machines that can be produced with no individual moving parts. It's a single part system, all printed out of a single piece of plastic, versus other types of door handles, which are several parts. And it talks about how they built it and how they designed it and stuff. And they got crab feet, crab legs, pinchers, pliers, other things that they've designed. And there's a guy who builds materials for shipping products that are based on metamaterials, because they're very, very lightweight and don't use a lot of material, but they're exceptionally efficient at packing and load cushioning and softening. So fascinating world. Metamaterials is not just optics and invisibility cloaks. It's a whole bunch of other stuff. And if you really want to get into a deep presentation on that, you can check out this one at Japan. and she goes deep into how they built all this stuff and designed it. And so, yeah, go check that out if you have time. There's also non-auxetic mechanic metamaterials. This guy Zhang et al. You can look up some of their papers. Those are really interesting designs that, novel designs that they're coming up with, and I think they're even working with AI to come up with some of these metamaterial designs too. Some of these are on the next level, man. Imagine just using these for building or construction. You could, get a bunch of these, maybe link them together. It's just amazing what you could do with the future of these types of metamaterials. People didn't think about metamaterials like this, but they're kind of like programmable machines in some ways. So I don't know. The future is just what people can do with their imaginations. Really, with this stuff, it's fascinating to think about, and especially when you're doing it on the nano level and the nanoscale. Again, we talked about crystals and quasi-crystals. We didn't really talk about quasi-crystals. So we talked about crystals and glasses, but we didn't talk about quasi-crystals where they're dense and regular on a macroscopic scale. Quasi-crystals are metamaterials, but they can have symmetries in like higher dimensions, which is fascinating. Daniel Shechtman discovered quasi-crystals, and it was called pseudoscience. He was called a quasi-scientist by the world's leading chemist at the time, a multi-Nobel Prize winner, Linus Pauling. So be careful about the newcomers and new ideas on the market. You got to let things vet themselves and evaluate themselves scientifically, and you can't use stigmas or judgment or your opinions to rule what's real or not, because you can end up looking like a total doofus in history. Quasi-crystals can be used for light trapping and communications technologies. You can check out this article by Eric Quinones of Princeton University, where they developed this quasi-crystal. They built it out of 1 centimeter rods and then blasted it with 1 centimeter wavelength microwave horn here, and it bent the signal at 90-degree angles without losing any signal quality. So quasi-crystals can be used in like junctions or other points inside of a photonic crystal or computer, a photonic computer, to bend signals at 90 degrees. That's fascinating that it can do that. And they also have weird symmetries, which are forbidden in nature, supposedly. And if you want to get a crystal that can resonate in higher dimensions or with higher dimensional things, then you might want to use a quasi-crystal, because they can have hyperdimensional symmetries. Ed Fouché, my buddy, talked about them back in 1998. That's how I learned about this and got into it way back in the early 2000s, studying, Area 51 research and people that were involved in that kind of stuff. So Ed was a friend of mine. Not sure I can vouch for everything that he talked about or everything he said, but he was right about quasi-crystals and metamaterials. Man, these are some fascinating materials, and apparently lots of research going on into them as far back as 1998 for him to hear about these things working at Area 51 and be one of the first people to talk about them in relation to the UFO programs, which is fascinating. Because that's a early on connection that proves that the military has been taking this very seriously for a long time. Now, this metamaterial came out, this bismuth manganese terahertz waveguide. There's a TTSA and the U.S. Army have a CRADA agreement, which should be up soon with some results from whatever happened with this. The deepest that put off really went into it was this paper by Victor Podolsky talking about this metal mirror, metal and dielectric filling. So you have a mirror on each side and then a dielectric in between, and that is a wave propagation for these left-handed metamaterials. So you can pump then light into this left-handed metamaterial between two mirrors and get some interesting effects out of that. Apparently, is how these things bend space-time, or cause these space-time distortions with these quasi-particles that exist in these two-dimensional layered materials. Now, when you have layers of one thing of one thickness with another thickness, and these different refractive index materials, you could produce what's called a Bragg mirror. Bragg reflection is an interesting phenomenon. It will take an impulse wave, as in case of the Chichen Itza pyramid, and the acoustics of it is a real-world example of an acoustic Bragg reflector, where the impulse signal of a single clap is reflected and makes the sound of a bird, or a bunch of high-pitched noises, which makes a much different sound. Of these are all the clap being reflected off each one of these subsequent wave fronts as it goes up the pyramid. So that is an interesting example of what this does to an incoming signal, and how it could break it up into a bunch of chirps or pulses, and maybe those combine somehow backwards to create a giant pulse. Of course, we're looking for a pulse that's big enough to break the Schwinger limit, or cause polarization of the vacuum energy, in which case that's how you'd build a warp drive. You can also use these to build photonic circuits, which is super cool. Photonic circuits is like electronics, but you're using electrons you're using photons and excitons inside of materials instead of pushing around electrons. Much more efficient, less energy. You don't waste as much energy. Dimensional crystals, I talked about the Vantablack and the carbon nanotubes, but there's other types of dimensional crystals as well, which affect things in not just one dimension, but or surfaces, but 3D. And some of these kinds of crystals in the 5D crystal structures can be used for permanently 5D data storage. So spin glass is one example of that. Spin glass is an example of a glass where the spins are locked into shape. So you can program the spins and then use those to program information into store information on a spin glass, and then later go back and look at the spins to read that information. So spin glasses are very interesting in that regard. And advanced spin optical glasses are just one class of these three condensed matter phase materials. A Fermi liquid being this disordered state over here, the quantum critical state being these things called strange metals. The strange metals are interesting. The spin glasses are cool for data storage and other things, but the strange metals are also interesting because a strange metal, they built one actually they took a sheet of a very thin piece of YCBO, superconductor material, and they punched a bunch of holes in it in a pattern, like a real ordered metamaterial. So they made a metamaterial out of this by perforating it with holes in an order, and that turned it into a strange metal. Now, a strange metal has, as Lenny Susskind pointed out in his lecture, a strange metal is topologically equivalent to an extremal black hole. So when you want to talk about creating, black hole-like structures, or these warp field structures in these craft, some of these materials might be something we might want to look deeper into. Could we build an invisible craft that warps the space-time around it without a metamaterials? Sure, someday. In fact, if the aliens come here, they're probably flying around in something like that, and it doesn't violate physics or the laws of Einstein. In fact, it's directly in accordance with that. But Jack has also pointed out the idea that this is a force field. Jack Sarfatti, who's going to speak very soon, pointed out that metamaterials also can be used as a force field. Now, the first force field that we've seen experimentally anywhere was observed apparently at the 3M tape factory. They had a very large sheet of cellophane tape that was traveling over a doorway in a certain area of the facility. And it's like a big thing of tape prior to it getting cut. And what that did is it created like this invisible wall that people reported hitting when they tried to walk under it or through it. And Now that's fascinating if true, and more research should be done into that and how we can go about building it. In fact, more research is being done by some people on our team who brought that to my attention. So thank you guys for that. Now, these quasi-particles in between mirrors are super important for a number of reasons, which will be talked about in the lectures to come. One is the ability to build polariton lasers. So this is a polariton laser diode, and these are used in the directed energy weapons like the nose cones of these hypersonic missiles and torpedoes and stuff that have been talked about. The next gen Mach 10 plus hypersonic. So they supercavitate the air in front of, or water in front of the nose cone and create a vacuum bubble, which they then fly through the vacuum. So this technology wouldn't be possible without these next generation laser systems, which are themselves built upon metamaterials. So again, it all comes full circle: super lenses, super materials, and super space age capabilities. The future is in our hands, and if people want to believe that all UFOs are just explainable natural phenomenon and nothing extraordinary, you can go on and believe that. But the truth is, I think you've seen it right and clear in this presentation. So thank you guys for watching, and remember, the reality of this is much, much deeper than anything you'll ever see on television. Thank you.
One hour. That's good.
1 hour.
Almost exactly.
I almost nailed it right on.
Good work.
You're muted, Tim.
Oh, sorry about that. Awesome. Let me bring everybody in. So guys, let's do an enormous applause. Enormous applause for Mr. Jeremy Rys. Man, I genuinely cannot thank you enough for pulling all that together. That's all new material too. That is all. I mean, and you, I mean, dude, this is like your skill. I mean, this is why the alien scientist is famous, because you were able to go through and just pull out this data and turn it into this cohesive presentation, right? That just blows people away. So thank you. I genuinely cannot thank you enough. So David Chester is up. Yeah, Jeremy, I don't know. Do you want to take questions? Should we go through some of the questions, or should we just jump right to David?
Yeah, I can take questions real quick if you want. I'm sure there's a few, but
okay, yeah. And if anybody, I mean, guys, if you know, Mark or Jared or David, if you guys have any questions, that's cool. And then, you know, I'll go through some of the comments here. We've got, you know, Joe says, very nice job. We've got Derek clapping, Ghost Rider clapping. So we've got some good stuff on there.
Yeah, if anyone in the chat has a question, just type in all caps. I can see your questions here too. So
yeah, that was a very good balance of being comprehensive yet understandable.
Yeah, thanks. I put a lot of there's just going to be more stuff as the research continues into it. I mean, I haven't touched this topic in a while, and just putting this together, I was finding all kinds of new, interesting things that are going on in the world of metamaterials. You know, there's this insider trading scandal going on with the MAT stock or whatever with the SEC and everything. I didn't include that or talk about that, but yeah, there's lots of missing money and budgets and stuff like that, and people that made a ton of money off of their investments and stock options and stuff again. So yeah, there's a lot of classified stuff going on with metamaterials that people shouldn't sleep on, the science of this.
Yeah, and actually, I'm going to put this up real quick. So Remnock was asking, is anybody working on the inertia mass canceling craft? Is given there? Look, see, Mark, and I should mention. Let me jump.
Yes, we're actually replicating that, and we got a spin forming machine in order to make the inner and outer hull, and that's an experiment in the works here at Falcon's base. Yes.
Yeah.
We're working on that.
And
we're going to do two variants. We're going to do a like a saucer shape. And Tammy Padina wants to try a triangle shape as well, as shown in the patent. So it'll be like flat edges. So one's going to be sort of curved and one's going to be flat. We'll try them both.
And so I should mention in open mic, and this is on our YouTube channel, John Brandenburg last week ran through some really interesting stuff about Sal Pace work, especially relativity theory. And then I'm fingers crossed, right? But fingers crossed, I have an interview with Sal tomorrow, and we'll see if we can pull that one together. So, so I think, yeah, I mean, I think in terms of, let me see. Let me see. Here's one. True Seeker was asking, have read the paper from the UFO theory group on geodesics, and what is your opinion? And that one he might not know offhand. That's a
No,
little obscure.
haven't read it yet. I'll have to check that out. What's it? UFO theory group?
Yeah. Oh, UFO. Yeah. UFO theory group on geodesics. So that might be one to take a look at if you can find it. And then another one here is, let me see. I got somebody who said, oh yeah. So Kung Fu, they're telling you, Mark, you need to give them their dog back. Nobody wants my dog. But my dog is well behaved. That's why. And then Jeremy, have you ever checked out Burckhardt-Himes theory? So Heim theory, and that's something I'm a little familiar with. Gary Stevenson did a lot of work on Heim theory.
Yeah, I don't know too much about it. You know, I've again, it's just another theory that's out there, and we got no shortage of theory, and we need more people to jump in the lab and test these theories out and get something working with it. But you know, we got some of the best theorists out there, so I would if you're into really good theory, I would just buckle up for this next presentation.
Well, yeah,
Can I ask Jeremy a question?
Oh yeah, go for it, Jared.
So Jeremy, you mentioned a bunch of uses for metamaterials for cloaking, and then you mentioned some for propulsion. If you had to give it a balance between the two, how you think these are being implemented and used in the UAPs, which do you think they're used more for? Do you think they're used more often for the cloaking, or do you think they're used more for the propulsion?
Well, I know that they're used for the cloaking for sure. I mean, we've developed that and shown that. But as far as the propulsion, I think that remains to be shown experimentally. You know, so it's definitely theorized that they can be used for, you know, propulsion. You know, in terms of we use these dielectrics and a lot of these other machines. You know, for activator cavities. So if you have a super dielectric or a negative refractive index material, that might be you know, more suitable for those types of experiments and stuff. But yeah, I don't know. It's hard to say until without more data on their use in other things.
So I just dropped a copy. I archived this, right? And this is one of those things that you save when you come across it. The UAP theory website. That was what they were talking about. Thor's UAP theory. He took that down. There wasn't any nefarious reason. He didn't want a lot of publicity. I talked to him about it several times, and he said he was starting to get questions and emails, and he's like, my email box is overflowing. I'm done with this. And so I'd actually asked him, I said, man, this is brilliant work. You got to save this. And he's like, okay, well, just download it. So there it is. It's in a zip file. He has GIF images, and what he has supports, I guess, what Jack Sarfatti is talking about. And actually a lot of the stuff that Jeremy's talking about today supports it too. So there's a lot there. Although, you know, there's so many different approaches to this. And like Mark, for instance, Mark is working on a couple of different projects, but those are different approaches, equally valid in their own way. They're just different. Mark is running off to get something. That's terrifying. He's going to come back with something that flies. So, well,
hey Tim, do you mind emailing me that website when you get a chance?
Oh yeah, yeah, absolutely. Yeah. It's yeah, again, it's just it's in that chat thing. I hear Mark rooting around in the back. So, um and you know what, in just a moment here, David, I definitely want to I definitely want to go to you. There's Mark. Mark, do you have something to share? I thought you were going to come back with something flying.
Oh no, not right now. Somebody just came to the door.
Oh, okay.
Oh, okay.
Okay.
But we'll
Well,
do that later. I actually have an experiment coming up that was Todd DiCiotto's inspiration. Something about figuring out whether his theory is correct. We're going to having opposing magnetic fields and weighing a sample inside of it. He expects the sample to grow in weight, but I'm going to get that set up on the other computer on OBS, and we'll have it for you guys later after David Chester and Jack's presentations.
and again, all of you guys, it doesn't come across in the APEC conference, but you guys are doing amazing work, tons of it. So, okay, well, let me do this then. It is I want to go to David, so I'm going to remove everybody out of here. And Jeremy, thank you again so much, man. Thank you again. I genuinely, you saved my bacon on this. It is wonderful to be able to put this up. There's so much there. People are definitely going to be wanting to replay this. Okay, so David, thank you, sir. Thank you. So basically your paper, this is something you presented at the Sarfatti Cortona webinar. Again, that's up on the Alt Propulsion channel, and there were a bunch of different presentations there. But this is a quantitative analogy between gravity and condensed matter, right? Where you're looking at several different theoretical approaches to basically modifying the fabric of space-time based on the formalism of relativity theory, quantum mechanics, and other models. And as I have told people many times, like your work in physics for me has been inspirational. And I know I'm brown nosing, it sounds like it, but I just very quickly, I know lots and lots of physicists, and typically they have one, maybe two pet theories that they push for everything. The thing that I love about your work is that you're able to do meta-analysis across 10, 15 different theories and compare them, which is just unheard of. So on that note, David, I will remove myself from it. And do you want to put up there? There we go. Let's add your stage, and feel free to take it away, sir. And thank you so much.
Thank you very much for the introduction, and thanks to Jeremy for that amazing talk, which actually set it up for a great segue, because today I'm going to talk about a quantitative analogy between gravity and condensed matter. And so there's actually good motivation to do this, because we want to use metamaterials or just condensed matter, just materials in general, to do metric engineering. So we're going to need this collaboration. I'm assuming that it's not going to be something where one person figures it out. I think we're going to need a big collaboration to figure this out, especially if we want to scale it up to make something that's really useful for the whole world. I think it's going to be a collaboration between gravitational theory and condensed matter experimentalists. So to do this, it's very difficult because we need to find some common language. So rather than talking about my proposal for how to reach anti-gravity, I'm going to try to lay down a foundation for that common language. And another motivation to do this is that we might want to do numerical simulations along the way. And so looking at some of the discrete structure of relativity, and when you discretize it or approximate general relativity, a lot of that language is going to be very helpful because it's analogous with atoms and lattices and crystals. So the analogy that we're making is that we can think of atoms of space-time. So the idea is that in flat space-time, you typically have what's called Minkowski space. It's still relativistic, it's special relativistic. We have space and time, but we're imagining it as this four-dimensional crystal. And the gravitational fluctuations, which are found in general relativity, such as gravitational waves, those are going to be found as defects away from the crystal. So you can see how this is a very different language of gravity than is typically spoken with all the differential geometry, that now it's putting it more in that condensed matter language. And so there's a lot of ways we can actually approach GR. And so what we know for sure is general relativity is a good theory at low enough energies, but we still don't know what the best high energy theory of gravity. And when I say high energy theory of gravity, I really mean quantum gravity, what most people call quantum gravity. We're not even sure if gravity needs to be quantized or not. So that's why I call it high energy. And so at the same time, we want to respect Einstein's legacy, in my opinion, because we certainly learned a lot from Einstein. So we don't want to just do something that's too simple, because Einstein did bring some complications. Unfortunately, his theory is complicated, but I think that a lot of those complications are reflective of what we see in reality to a solid approximation. So just to see how we can learn from history, I think it's important to review the development of electrodynamics. And this is another example of a theory where we have Maxwell's equations. They're valid at low energies. And this theory was found in the 1800s, and it's celebrated as being the most successful theory of electrodynamics. But now with quantum electrodynamics, okay, that's one way where we expanded Maxwell's theory into the full quantum theory. But we also know that quantum electrodynamics shows how Maxwell's equations break down above the Schwinger limit. And that's actually one of the things that Jeremy was talking about, is when you reach high energy electromagnetic effects, you start, basically the quantum effects start becoming classical, and that leads to a breakdown in Maxwell's equations. And it's still all good. We're not saying that Maxwell was wrong. We're just saying that Maxwell was approximate, and it was the perfect theory, the best theory you could write down at low energies. But we now understand that there's this bigger framework. And a lot of the reason why we were able to do this and get this quantum electrodynamics was because Maxwell's theory was a gauge theory. And so this turns into a lot of complications. I'm not even going to say exactly what a gauge theory is. I mean, really, I will. It's just a theory with some local symmetry, typically described by a Lie group or Lie algebra. I mean, that might not mean too much to people, but just it's okay. Just trust me. Even the experts had some confusion about this, because Paul Dirac is one of the greatest physicists, and I mean, maybe he wasn't confused, but the way he defined gauge theory is not what I am talking about when I say gauge theory. He had this notion of defining gauge theory in terms of these Hamiltonian constraints, and he found this nice analogy between electromagnetism and linearized gravity. And linearized gravity is just a low energy approximation of general relativity. And so while Dirac's notion of gauge theory had a lot of nice mathematics that was helpful, in the modern sense of the term gauge theory, this is not a gauge theory. Linearized gravity is not a gauge theory, and general relativity is not either. And the way I use the term, the reason why this is true is because gauge theories have some additional structure. So typically in general relativity, we have this notion of space-time, right? And then now we're going to introduce some additional structure with electrodynamics. There's this U1 gauge symmetry, but really it can be anything. You can have other gauge theories, and this is used for the standard model, and this describes quarks and the strong force and the weak force. So it's not just math, it's very much confirmed by experiment to this day that this gauge theory is good mathematics. It leads to good physical theories. And there's a wide class of gauge gravity theories that limit to general relativity at low energies. So just to put this analogy further, there's this notion of a covariant derivative, and this gets used in Maxwell's theory. It gets used in Yang-Mills theory, which is what's used for the strong and weak forces, and it also gets used in gravity in just slightly different contexts. But in gravity, there's this notion of this connection, which tells you how to transport when you have this curved manifold. It tells you how to move around. And Yang-Mills theory has these Yang-Mills fields called gluons, and those enter the covariant derivative there. So this really starts to see how the mathematics of gravity can actually look very similar to a gauge theory. And so if you want some motivation for gauge theory, it's maybe people don't talk about it enough, but a lot of the modern attempts to quantum gravity are all using gauge theories, whether they fully realize the full implications or not. I mean, supergravity and superconformal gravity, those are gauge theories. They're gauging the super translations. Okay, some buzzwords there. And then string theory and M theory also limits to those. So even if those theories are right or wrong, they're still gauge theories. And loop quantum gravity is probably the second most popular attempt to quantum gravity, and that's also a gauge theory. And then you can just go into the literature and find all these other different gauge theories. Then it gets confusing to classify, because then there's this gauge theory of gravity, which is different than these gravitational gauge theories. There's all these terms out there, and there's all these theories, but basically the idea is some type of gauge theory of gravity will be good, but how do we figure out what the good one is? And really what I've been thinking about is, how do we respect Einstein and Dirac's legacies? And really, if you think about Einstein, he had this notion of diffeomorphism invariance. And that's what Dirac was trying to get with his mathematics. But honestly, he was just too early when he was doing that work. It was just too early. I mean, this is 70, 80 years later that I'm able to make some of these observations. So it's not really their fault per se. But now there's a lot more work in the there's a lot more work that's been published, and it shows how you can get this diffeomorphism group as a gauge symmetry, and it would limit to general relativity at low energies. And so this is something that's pretty complicated, but I really do believe that this is a good, solid idea to pursue. And if we pursue this and try to figure out how it works, it turns out it forces us to actually think about this analogy that I'll get into with condensed matter. And so I'm going to just skip this slide because there's difficulties with it. But the basic idea is that we have general relativity, and then there's this notion of conformal gauge gravity that gets talked about in the literature, and then there's also this notion of metric affine gravity. And so when you go into the literature and you try to understand the classification of these gauge gravities, there's kind of this schism where the pure gravity community kind of embraces this metric affine gravity more, whereas maybe the supergravity community latches a little bit more onto the conformal gravity. But you don't need supersymmetry to study conformal gravity, and certainly tons of gravitational researchers are studying conformal gravity too. But it turns out that there's actually a way to understand how these two things are brought together by the diffeomorphism group. However, this diffeomorphism group is infinite dimensional. So naively, you might think that it'll lead to an infinite number of gauge fields at first glance, but it turns out it doesn't seem to be true. But basically, even the world experts, there's just very few people that are even aware of how to think about turning this into a gauge theory. So it's difficult stuff, but it's good. I mean, the good news is that actually the thing that's the same in conformal gravity and metric affine gravity is this scale transformation. And that was introduced by Hermann Weyl in around, I believe around 1918, and he introduced it for a unified field theory that would unify electromagnetism and gravity. And that theory was shut down by Einstein, but actually Einstein's refutation was completely false. So basically what I'm saying is that this structure that is in both the conformal group and metric affine gravity was introduced originally for unifying electrodynamics and gravity, which is fascinating. And so just to motivate what I'm about to get into, which is torsion and non-metricity, I like quantum field theory and general relativity, and these things have really been used for two of the biggest experiments that humanity has gone into, which includes the LHC, which detected the Higgs boson, and LIGO, which detected gravitational waves. So obviously, these were examples of huge collaborations that required a combination of theory and experiment to come together. And something my PhD advisor was able to figure out is that there's this method called the double copy. And this relates Yang-Mills theory, which is a gauge theory, to solutions of general relativity, which is pretty remarkable because these are the two different theories that we're struggling to bring together. It turns out their solutions are related. And the picture gets even deeper than this. There's actually this web of dualities between different theories. And there's 6 different theories I'm highlighting here. There's actually way more that fit into this picture, but I'm just going to focus on 3. Basically, general relativity is right here, and there's this color kinematics duality that my advisor found that allows us to find general relativity solutions from Yang-Mills theory. But in this network as well, there's this Born-Infeld electrodynamics. And that theory is actually the renormalization, the one-loop renormalization of Maxwell's theory that I was mentioning. When you go at high energies in electrodynamics and you go beyond the Schwinger limit, the classical theory of electrodynamics breaks down, and you need a nonlinear theory of electrodynamics, which is this Born-Infeld electrodynamics. So it's very curious to see how right next to general relativity, there is Yang-Mills theory, which is this gauge theory, and then Born-Infeld electrodynamics, which we know might have applications to understanding warp drive. So it's also worth pointing out that when you do this double copy, you don't just get general relativity. You actually get what is called the axion and the dilaton. So you get these additional gravitational particles. And the axion is actually a candidate for dark matter, and maybe the dilaton relates to a lot of different cosmological applications for dark energy, perhaps. But it was puzzling because it turns out that this axion and dilaton actually has a gauge gravitational origin that was talked about. Actually, there's work, Tucker and Dorelli talked about this in the 1980s, but actually the pioneers of string theory and supergravity talked about this as well in 1974. And the entire string theory community doesn't even really understand this. So it's one of these things where the pioneers did the right mathematics, and they're not embracing the geometry of these gauge theories to their full extent, which is leading to issues with quantum gravity. And it also, when you understand this differential geometry that's associated with the axion and the dilaton, it starts to clarify a lot of things in this condensed matter analogy. So just to reiterate what's here on the slides, the axion is known to be associated with torsion, but it's also known that the dilaton is associated with non-metricity. So this notion of curvature, torsion, and non-metricity are the full scope of what gravity can offer, whereas general relativity just has curvature. So this is what I say when we say we want a more general relativity theory, right? What could be more general than general relativity? Well, it would be a theory that has curvature, torsion, and non-metricity. And Elie Cartan was the one who introduced torsion, which Einstein became very fond of. And then, as I was mentioning, Hermann Weyl introduced non-metricity, which there's a lot of interesting work showing how it's useful for the origin of mass and cosmological implications. So it's very, very rich stuff here. And there's this theory called metric affine gravity that I was mentioning, where it combines all three of these into a single framework. And it's actually not one theory, but actually a collection of theories. It's more like a framework that allows you to give different theories and explore. And so this more general theory actually contains three different theories that are equivalent to general relativity inside of it. One of them is just Einstein's general relativity. Another is this metric teleparallel equivalent. And then there's this other symmetric teleparallel equivalent that the first theory has curvature, the other just has torsion, and the other just has non-metricity. And so this is very exciting because these are things that have been talked about very recently, but we still don't even have work that really understands how to go between these different theories when we're dealing with matter. There isn't yet a consensus in the community about how to deal with matter within this entire framework. And you could see why this is very important, because we're trying to use matter, such as metamaterials, and understand how that leads to how do we modify space-time. And so if we can't figure out how matter affects all of these things, then if it turns out these things are important, then we're going to be missing a part of the puzzle. So our goal here for this whole conference, well, maybe it's just alternative propulsion. I've just talked about anti-gravity. Maybe I just focus on that a little bit more. But that relates to this idea of metric gravitational engineering. And so we can't just, we have to stick to some theory. You can obviously do whatever you want in the lab. That's totally, it's a free world. But if you want to understand the mechanics of what's happening at a mathematical level, then, we're going to have to be very careful and take a somewhat conservative approach, because there's a lot of bold claims that get stated, and just because you have a bold claim doesn't mean that it's correct. So we've got to get grounded in something. And so I'm not really trying to provide a solution on how to implement anti-gravity, but really just motivate what we might want to look into to really develop that tool set so we can try to figure out what's going on here. And maybe you guys have seen the slide before, but anti-gravity is hard for a good reason. So in Einstein's field equations, there's this factor of 8 pi times g divided by c to the fourth. And when we use these man-made units that we use every day, the Newton's gravitational constant is a very small number, 10 to the minus 11. And the speed of light's a huge number, but it's in the denominator to the power fourth. So by the time you multiply all these things together, we got something 10 to the minus 43. So the problem is that we can use energy, momentum, and stress of matter to source space-time curvature, but you need so much matter just to get the tiniest amount of curvature. And that's really the issue. And so obviously there's this Alcubierre drive that says, hey, if we just had negative energy, then we could get warp drive. But even if you had this negative energy that we don't know if it exists or not, you still would need so much of it just to get these effects. So that's why it's very challenging to get true anti-gravity in this sense of modifying how gravity works at the fundamental level in the equations. It's going to be very difficult to just tinker this. Even if NASA found something in the labs and it's exactly correct, even if I don't know if what they did was correct, but even if that was correct, you can tell They even had theory that matched their experiment to an order of magnitude, but it's not a good enough match, because if you scale that up, that was the problem. They got a tiny piconewton force that they measured in the lab, and it's such a small force, it's hard to evaluate if that's a real effector or not, or if it's some error, right? And so as soon as they tried to scale it up to something that would be on the real scales that we need, the mismatch between theory and experiment got worse, and it didn't work, and they didn't know what to do with it. So it's hard, right? And so if we're gonna this is the thing. People are saying, "Hey, stop talking about all these complicated theory." Well, no, actually, everyone's very respectful, to be honest. But I get it, right? I'm this theorist. I'm not that connected to experiment. I should be trying to distill it down so engineers can work with it. But here's the problem. I mean, if you just look at other fields of engineering, if you go to engineering school, you learn physics. So you learn Newtonian mechanics for mechanical engineering. You learn Maxwell's electrodynamics. You learn the aerospace engineers have to learn a lot of physics. And so if you're going to become a gravitational engineer, we might need to, maybe it's not quantum gravity, but that high energy gravity, we might need to understand it, right? So just to go through some of the basics of general relativity, we have space-time unified into 4 dimensions. We have the metric of space-time, and this is measuring infinitesimal lengths on the small scale. And so this metric tensor is what encodes all of the physics in general relativity. You can actually calculate the curvature from the metric tensor in general relativity. And so in flat space-time, you usually typically measure length if in space as you just square all of the lengths, like Pythagorean's theorem. Time brings in a minus sign, and this is in flat space-time. So in the curved space-time, it's just this general 4x4 matrix that gets used in here, and it gets contracted to give this quadratic form that leads to the length squared. And then you could take the square root of that, and then that would give you your magnitude. And so that's how we measure lengths. And then there's this connection that stems from the covariant derivative, as I was mentioning. And this helps you figure out parallel transport and figure out, someone was mentioning geodesics. So there's this geodesic equation, and that tells you how matter moves. It follows the geodesic path. And this tells you how it moves. It's basically saying how gravity is a fictitious force. I should mention that in general relativity, just to introduce what non-metricity and torsion is, non-metricity is the covariant derivative of the metric tensor, and it's assumed to vanish general relativity. And then torsion is this anti-symmetric component. You basically take one version of the connection, and you just play with the indices a little bit, and then you put a minus sign, and that's the torsion tensor. And this vanishes in general relativity, at least in the 1915 formulation. And so you can actually, when you use this general relativity, you can derive the connection from the metric tensor. So this is how you do it. You take this partial derivative. So this is getting into the calculus of the differential geometry. And we have this covariant derivative and the geodesic equation again. And so once you have the connection, you can compute the curvature tensor, which, so these are indices. They all, just to remind you, they run from 0, 1, 2, and 3 for time and space. So this is a 4 tensor, which has 4 indices. So it's not a matrix. It's even larger than a matrix. It's like a 4x4x4x4 object that you can envision, and it's encoding a lot of rich information about the curvature of space-time, such that we can take traces, right? Like when you have a matrix, you can take the trace by summing over the diagonal components. And so you can do the same thing with this Riemann 4 tensor. You can take a trace, and you get this Ricci 2 tensor. And so this thing is like a matrix now, because it's got it's got rows and columns, and the rows are one index and the columns are the other index. And so you can take the metric tensor and contract the indices, which is very similar to the trace. And now you get your Ricci scalar. So this is just a single number. There's no indices. It's very simple. And so the Einstein-Hilbert action is pretty elegant and simple, because it just involves this Ricci scalar, no crazy tensor analysis. But the remarkable thing is, when you recognize that the metric tensor is a field, a gravitational field, you can apply Euler-Lagrange equations and derive Einstein's field equations. Voila, here we go. We see that 8 pi times g over c to the 4th, T mu nu is the stress energy momentum tensor, and g mu nu is the Einstein tensor. And there we go. So that's it's the second order differential wave equation, because we have the metric. We take one derivative to get the connection, and then one more to get the curvature. So there's 2 derivatives in this wave equation. just like Maxwell's theory, except now it's nonlinear. It's a little more complicated. And so if you specify what the matter sector is, if you have a theory for what matter is, then you can actually derive what the stress energy momentum tensor is by varying the action with respect to the metric. And it's very curious to think about the history. Why was this called a stress tensor? What's the meaning of this? What does it actually mean? What was the first theory of physics that had a stress tensor? And it was elasticity theory. And so you could ask, what does elasticity have to do with gravity? I mean, well, in the 1800s, it was thought that the ether was this elastic medium, right? And Einstein replaced the ether with general relativity, more or less. And so what's really remarkable is that this metric affine gravity with torsion and non-metricity is claimed to be relativistic elasticity theory. So I find this beautiful because we're still respecting Einstein, and we're not saying there's an ether, we're just saying that there's this relativistic elastic medium that has gauge theoretic properties. And then you can play games on whether this ether is actually physical or not, right? It's just this gauge redundant information. Maybe it's not real. I kind of actually believe it is real, but most people think this gauge symmetry is just redundant information. So it gives you an ether, and you can pretend like it's not there, which is great in my opinion. So basically, you can just review some of the fundamentals of elasticity theory, and you start to realize that what Dirac was thinking about in terms of the gauge transformations in linearized gravity is very simple. It's very similar, I should say, to the gauge-like transformations in elastic theory. So really showing us that something about space-time is more like materials, because we use elastic media are just objects in the material world, right? And so to get into this analogy that I'm talking about, basically Hagen Kleiner is this pioneer because he's just really smart guy who understands condensed matter theory, he understands gravity, he understands gauge theory, he understands a lot of things and has published a lot of great work. And he found that torsion is actually necessary for Feynman's path integral of hydrogen. Feynman didn't even teach he didn't even teach the path integral in his books because he couldn't figure it out for hydrogen. And so this was a huge problem. And it's because you need torsion, which isn't in general relativity. And so he worked out this analogy of world crystal defects. So typically we say a material might be like a solid, might be a crystal. And now, so a world crystal is to say the world, space time is actually like a crystal and gravity is like defects. And so, I'm thinking that this is really showing how space time is like a material. I'm not saying he said that this was an ether theory, but that's kind of what it looks like, right? And so when we start pursuing this more seriously, we actually have to generalize it to get the non-metricity, because he just dealt with torsion for the most part, but he articulated that, it could work for non-metricity as well. And physicists don't like working with this because it makes us think very hard about how to define lengths and angles. Basically, non-metricity messes with lengths and angles. And the way I think of it is it's kind of like driving a Ferrari to some degree. Like it's a nice car, it's a nice theory, but you really need to know how to use it in order to get anywhere, right? So you can imagine a ball rolling down a hill. And if you go to study classical physics in high school, or maybe first year, second year of college, they'll tell you about how to solve these problems of a ball rolling down the hill, but they'll typically make an assumption that there's no friction. So there is friction, but there's no slipping. So everything is sliding and there's only that friction, or you'll do rolling or you'll do sliding, but they'll rarely tell you how to combine both. And in general relativity, there's this manifold and then there's this tangent space. So as far as I understand, it seems like these metric affine spaces are allowing for this ambiguity where you can have the tangent space where all the vector fields are living, all the fields that we know of, they're being put on space-time. But the way it's put on space-time it can slide or roll and slip in this more general framework, and it makes it very difficult to get our grounding, which is why a lot of people don't like to look at it, but I love it. And so basically, the affine linear group is the most general sense of linear transformations that you can have on a vector, and that's the gauge group for this metric affine gravity. So it's pretty straightforward. You just have this it takes some time to learn all this stuff for sure, but it's a 4x4 matrix that we have right here, and we're just doing a matrix multiplying by a vector here, and then we're adding a shift. So this is kind of like an extra dimensional version of y equals mx plus b, right? You have this generalization of the slope here that also adds in rotations and shearing. And scale transformations, like a slope is kind of like a scale transformation, it just multiplies by some magnitude. And then you could translate as well. Like if you shift everything over by a constant, that's what this b mu is doing. And so these transformations are described by metric affine gravity. And you can break it down further. There's if you remove the translations, that b factor, you just have this general linear group, but you can simplify it further and break it down into these irreducible components where you have the rotations of space-time, and that leads to curvature. But then there are these shearing transformations that allow you to skew things, and those relate to non-metricity. So you can see now how non-metricity allows for a more elastic, because elastic media allow for shearing, right? They can kind of deform and oscillate in different ways. They're not just rotating and getting translated. So while general relativity space-time is more rigid, this metric affine gravity is a little more flexible. Maybe it's flexible for describing exotic phenomena. All right, so we have these gauge gravitational field strengths of curvature, non-metricity, and torsion. And it gets a little complicated, but this is the simplest way I found to organize it all together. So if you recall, there was this Levi-Civita connection that used these derivatives times the metric, and that goes in here for general relativity. And if you take that torsion tensor and non-metricity tensor and you just align the indices in the same exact way, you don't even have to think about it. And then you get what's called the contortion and disformation. And this enters this more general affine connection. So basically, you typically have this connection, but now the torsion and non-metricity gives us a new connection that makes everything confusing, because now we can think about this connection or this connection, and get in all these debates for decades over how we should actually move around in these spaces, right? Like there isn't a great consensus that everyone agrees upon on how to use this mathematics, because there's so many good ways to use it. But that doesn't mean we shouldn't just use it. I mean, we should try to figure out what the best way to use it is, in my opinion. So the geodesic transport uses that Levi-Civita connection, but the auto-parallel transport uses the affine connection. And the confusing part about it is in general relativity, these concepts are the same thing, because the affine connection is the Levi-Civita connection, because there's no torsion and non-metricity. So when you write textbooks based on general relativity and you just pretend these concepts are the same thing, it starts to get a little confusing when you want to go into these more complicated things. But basically, the geodesic path, as far as I can tell, the best interpretation I found is the geodesic path is the true path that would get taken, but it won't give you the true transport. So the auto-parallel path is a different path. It's not the physical path that gets taken, but that path will transport the fields to their final destination in the correct way. So in my opinion, I think both of these types of transport are useful for characterizing all of the information on how to transport fields in space-time when there's gravity in the most general sense. And so we're going to get into this notion of holonomy, which involves transport around loops. And here's just some more mathematics. It's just a fancy way to write it in terms of differential forms, but let's not worry about that. And so the other cool thing about this metric affine gravity is it gives us more sources of matter. And this is very interesting because this gives us another opportunity to think about how can we respect Einstein's legacy, yet still do something a little more exotic, a little more advanced, to allow for more exotic structures. If we have these complex metamaterials with all these things at different scales, and we don't even have the geometry to allow for scale transformations, maybe we're missing something. So you get this metric stress tensor, you can vary the metric, but then there's also this frame field that leads to torsion, and that gets sourced by this canonical energy momentum. And then there's this hypermomentum that gets found from the connection, which includes some of the non-metricity. And there's a few different ways you can define different matter sources. And even the inventors of this theory as well, they just put out a recent paper, and they kind of simplified it a little bit, because it gets complicated. It's hard. There's not a great consensus, but it's good mathematics. And I think we humans, we're not always perfect. So it just takes us some time to figure this out. But let's get back to basics. So we're just going to talk intuitively about what is curvature and how to characterize it. So imagine you just, you're very small scale. You're taking these infinitesimal steps, just very small steps. And let's just say you could go in that, you could step in the x direction. You're in this two-dimensional world, or you could step in the y direction. So typically, when space-time's flat, you walk in the x direction, you walk in the y direction. It gives you the same thing if you walk in the y direction than the x direction, right? It completes that square. And if you had a vector, you would transport that along, one way or another way, and you would get to the same vector, typically, in flat spacetime. But if you transport one way and one the other way, and it turns out that the transport leads to the vectors not being the same final vector, if one vector is a rotation to the other vector, I was mentioning that curvature relates to the rotational gauge degrees of freedom of doing rotational transformations, and this shows why. If your vector gets rotated from what you would expect, then that implies that there is curvature in the loop. And this also describes why there's 4 indices in a very intuitive way, right? Because there's 2 dimensions for this square, right? And though each dimension has an independent index. So I could go in the x direction as one index or the y direction as another. And then the initial vector and the final vector as 2 other indices. So that's why the Riemann tensor is this 4 tensor. And then, so you could do the same game where you translate around in a circle or you go in a loop. But what if you went around a loop and you didn't come back to yourself? You actually got translated. You don't even need to look at transporting a vector to see this translation. So you don't have to worry about transporting a vector. You can just transport a point. And if you don't get back to the same spot and there's a translation, then that means there's torsion. And then finally, this picture might be a little, I got to make this one a little better, but let's say both of these, they're defined in a loop. They're defined in a loop, but non-metricity is defined on an open line. So whereas torsion was defined, the torsion you would get is you're assuming that it's this infinitesimal loop and the torsion is constant over this entire area, which is a 2-dimensional conception. Now the non-metricity is defined on the line. So it's going to be this 1-dimensional thing, but it's still a 3 tensor, and we're going to take 2 vectors. So one vector has one index, another vector has another, and then we're going to transport along the line to get a 3rd index. And typically, the dot product of these 2 vectors would just be invariant, right? Lengths don't really get deformed, right? If I have a ruler in London and I bring the ruler to the US, it's still a meter, right? If you have a meter stick, let's say, right? So, but what if it turned out that you had rulers and the geometry of the rulers was deforming the rulers themselves, right? Sounds like you don't have a good ruler then, do you? And that's really why people don't like to work with non-metricity, because it doesn't make much sense unless you think really hard and make sense of it. And so you can get these scale transformations and shearing, and those would affect the lengths of things. So if space-time itself is oscillating and shearing like an elastic medium, and we're using space-time to measure things, then it means that space-time actually isn't a good measure because the rulers are changing. But just saying that space-time doesn't have non-metricity isn't a good motivation. We really need to introduce the mathematics and then motivate or solve or experimentally demonstrate that this doesn't exist, which people claim to do, but they're looking in the wrong place. It's because they're not looking into the condensed matter theory. And so, as I was mentioning, there are these 3 theories that are all equivalent at the classical level, and one has curvature, general relativity, another has torsion, another has non-metricity. So this idea that non-metricity isn't real doesn't make any sense because you can get all of the results of general relativity from this theory. So it makes it more complicated because you have to specify your conventions. And then this is just reviewing the definitions again and showing you have this rotation of an angle, this translation, and then the vector is getting deformed in length. And so this trinity of gravity is pretty deep. And here's just one, this is just showing the Lagrangian of the other theory, but who cares? You guys can look these up on the internet, and here's the references. And so you get all this exotic differential geometry, and then you can classify all of these theories on this cube, and you can get to all these different theories. But we have to think about what we want, right? And I think this idea of thinking of space-time as a crystal is very helpful. It's a good language to understand how these things relate to each other. And so there's going to be a correspondence between the defects and these field strengths, where the field strengths include curvature and torsion. And so basically, with the curvature, it's called disclination defects. And then with the torsion, it's called dislocation defects. Okay, these are just buzzwords. So I'll try to get to some pictures that show what these are. And then for non-metricity, they're called vacancy defects, or you can have excess defects. So I'll just explain what that is. So with non-metricity, they're the simplest 0-dimensional defects. They describe the geometry of adding or removing a point to space-time itself, which is it's the most smallest form. It's like a quantum of classical gravitation, if you will. So it's the smallest form of classical gravitation that you can have. And that's why we can't see it on the large scales, because it's so small. It's not going to have effects, especially when we're going to show through the defects, the interpretation is ambiguous. We already said you could replace general relativity with torsion or non-metricity. So the most conventional thing to do is to push everything you can to curvature. If you take all the non-metricity and put it to curvature, anything that isn't curvature is going to be in non-metricity that's left is going to be very small and difficult to detect experimentally. So it kind of makes sense why we're not finding this in astrophysics, because it's such large phenomena in astrophysics that it's not going to be relevant. These things are microscopic. They're going to be more relevant for particle physics, for matter, for condensed matter, atoms, crystals, things in the laboratory. And so it's a form of gravitation that would be useful in the laboratory. And so just to review some of the pictures for curvature as disclinations, imagine you had this cylinder and you basically cut out a wedge, and then you compressed that wedge together and you glued the edges together so it was no longer a wedge. And so you'd end up, the final picture would end up looking like this disc, but the geometry got deformed because typically you need to go 2 pi around a circle, right? Everyone knows this. There's 2 pi angles in a circle. You sum it all up, right? And 90 degrees is pi over 2, right? 180 degrees is pi. You go in a circle, you get 360 degrees. But what if you're in some geometry where it wasn't 360 degrees? That might imply you have a wedge disclination. And there's more exotic forms of disclinations as well. And I was just realizing, I think that these are actually non-Riemannian curvature. And this splay disclination, if you think about it, to me, it kind of looks like a shearing effect, whereas this twist is it's twisting in a way where I still need to derive exactly how this decomposes, because this is actually the non-Riemannian curvature that includes the contributions from all three. And I haven't seen any work that actually decomposes it yet, but maybe this turns out to be a contribution from non-metricity and this from torsion. That's my current conjecture. But anyways, you can see that right here. It almost looks like a square, but it's triangular. And that's because I cut out 90 degrees and glued it back together. And so I turned this square lattice into this weird thing where now there's some curvature right at this point. Because if I walked around this loop, I would notice that 90 degrees, everywhere is 90 degrees, but something looks weird. It's deformed. There's this defect, and that's leading to curvature. And so here's just a little demonstration of walking around the defect. And so you get if you started with this green vector and you transport it around and you just kept the vector the same, when you get over here, you'll realize it got rotated by 90 degrees because you cut out this 90-degree wedge. And the rotation of those two vectors shows you that there's curvature right there. And so this is another way to think about taking curvature, but you can also think of these as an infinite number of line defects. You could take out these slices, an infinite number of slices, to get this wedge, and each of those slices would be a different type of line defect, and that corresponds to torsion. So we see how torsion is like infinitesimal curvature. And so here's just a single line defect that we just cut out, right? Or you could add in a row. You could take away, or you could add, and it gives the same type of defect. And so these are showing it in the discrete space, but this is showing it in the continuous space. And so there's actually, when you get to 3 dimensions, there's a couple different types of locations. One is this simple line defect. There's edge dislocations, so-called. I don't know where they come up with these terms, but it's really annoying. I hate that I have to memorize all this jargon, but you got to do it. So there's this other one, they call it a screw dislocation, and it's basically like a parking structure garage. You park your car, you go up to the next level, you just go in a circle. You go 360 degrees, but next thing you know, you're higher than you expected because there's torsion in the manifold of space-time itself. And this makes the analogy very clear because we've all driven in a parking structure, which is made out of what? Materials, right? So it's this elastic medium, right? You can imagine the parking structure may be oscillating, but when you look at that parking structure, it's not oscillating very much, but we know it is just a little bit. And maybe space-time is doing that too. Maybe it's not so rigid. And so here's just another blurry image of taking a 2D slice out of the 3D. And so here's just another example. If you basically took out this line defect and you walked around a circle, you still can walk from this point 2 to 4. And so you go in a loop, But since you're missing a point, you end up translating away from where you expected to land, and you see the vector got translated, and that's how you know there's torsion around this loop. And so you can actually compute the torsion tensor directly right there. It's very simple. It's not too hard to work out. And so non-metricity, you get these vacancy and excess defects. So I removed a point here and I added a point over there. And you can actually add and remove points. And we see that non-metricity is like infinitesimal torsion because we can take these defects. If we want to make a line defect, we just sum over an infinite number of point defects because a line is an infinite number of points. It's very simple, right? It's not complicated geometry, actually. It's just thinking about points and lines. And so we could remove a point and add a point, vacancy or excess defect. And so you start to see how there's a correspondence between these defects and the characterization in terms of non-metricity, torsion, and curvature. You could take a defect, you could look at it, and you could say this is one wedge disclination, or it's an infinite number of line dislocations. I mean, what description you use that's the redundancy. I mean, the defect is what it is. How you label the defect, you have the freedom to choose, just as you have the freedom to choose if you want to characterize things as non-metricity, torsion, or curvature. However, there's one caveat. If you just add a point defect to space-time, it's going to be very difficult to describe that in terms of curvature because it's more macroscopic. So in my opinion, non-metricity is the safe bet, but nobody likes it. So we want to actually try to maybe put everything in non-metricity and then integrate out everything we can to torsion and then integrate everything out from torsion to curvature if possible, and then see, is there any torsion left? Is there any non-metricity left? Yeah, this is just summarizing what I was saying, right? So not all defects can be described as curvature, but we don't know what defects can occur as spacetime. But if we do take this analogy seriously, there's no reason to suspect. It's pretty bizarre to say, oh, you can only take a wedge out of spacetime, but not a point, right? I mean, I don't know. I mean, maybe it actually works that way, but to me, just thinking in terms of we're trying to get a mechanical description of what reality is, it's very strange to say, oh, you can only take out wedges but not points. It seems like a very bizarre constraint to impose. So this is just going through some complicated examples that we don't really need to talk about. I should actually look to see how I'm doing on time here. Sorry for that. Yeah, we're doing pretty good. I should just wrap up. That's a pretty good summary of the differential geometry. So let me just, I just had some more examples here, but they're really just summarizing the same idea. And so I'm just going to kind of conclude. I mean, there's a lot of literature. Actually, a lot of the supergravity and string theory people, they're thinking about crazy ideas, but they're just not quite connected to reality. And a lot of the math will be helpful. They're missing some things. And there's also been some interesting controversy in literature. And I wish I had more time to look into this, but I'm just going to conclude by saying that we know that there are these Alcubierre warp drives that need negative energy density. There's also claims of maybe the Casimir effect or Casimir forces being helpful for implementing this. Maybe there are claims that maybe that is a form of negative energy density. Then you could get into arguments on is the Casimir force even related to the 0-point energy or not? There's a debate there. And so some people are actually saying that in these equivalent theories with torsion and non-metricity, what appears to be negative energy actually isn't negative energy because it also depends on how you define energy. And as I was saying, there's these different matter sources that in the metric affine gravity, there's these different types of matter tensors, and they have different interpretations, and there's different games you can play on how you define energy. So I wish I had more time to look into this work and give a good overview on how to, really dive into the good stuff for anti-gravity, but I just don't want to say something that's wrong. I don't want to make any bold claims. So I figured I'd rather focus on that language so we can all figure out how to communicate. And then once we figure out how to communicate, then we can start talking about, how to actually build something. Because a lot of times it just gets very difficult. We'll start talking to people and, we have, everyone uses the same words, but they mean different things. So if we aren't using the same words, then it's going to be very difficult to reach our goals. So just to conclude, I'll mention that gravity can be viewed as world crystal defects. Non-metricity is the smallest form of classical gravitation. It was actually introduced to describe electric charges. Torsion was actually introduced to describe spin density. And spin density is dividing by the volume. And stars are very large. They have a big volume, so they have a very small spin density. But things like electrons have a very small spin density in comparison because they have a very small volume. So it makes sense that we want to think about electrons in some gravitational theory. Obviously, We know that electrons have an effect on space-time, and we know that their effect on space-time has to be very small, very, very small. Obviously, electrons don't have much gravity, but if they do, maybe they have a little bit of non-intrusive torsion. And if that is true, then we need to understand this for condensed matter systems, especially if we want to use matter to create effects on spacetime. So I hope that we can just integrate out all the torsion and non-intrusivity. I hope it isn't needed, because then we don't need to worry about all this complicated mathematics. But if it turns out that this stuff is real, then it might turn out that the only way to experimentally detect this would be to try to work towards anti-gravity, because everyone's looking into astrophysics. It's not there. And we're going to need a lot of motivation. No, there's no good motivation to start looking for this in experiment. It's too difficult. It's too low of a probability. But if you're already looking to modify space-time with materials, then it's the perfect place to look for it. So I'll just conclude with that. Thank you very much.
Awesome, David. That is absolutely remarkable. Let me see. Okay. Perfect. You know what? Let me bring everybody back in, and let me see. There's Mark as well. Guys, enormous applause for Dr. David Chester. David, thank you so much. Again, that's like a tour de force. And actually, I've been looking for questions. I think this is, people are going to have to go back through and rewatch this, right? But this is so valuable. So thank you. I genuinely cannot thank you enough. And again, we've got just tons and tons and tons of clapping going on here in the comments. I'm going to put this up. I did see one question about orbital angular momentum, and it's scrolling up, so I lost it.
I have a quick question, if I can.
Yeah, go for it.
Have you seen the latest updates from CERN regarding antimatter falling in a gravitational field, and how does that relate?
I actually haven't looked into it in detail yet. So yeah, it's
just this week.
Yeah, so I mean, I might have saw a headline, but I haven't really like studied it. So I should dive into that. I mean, yeah, I mean, there's a debate on, because antimatter, there's this minus sign where effectively there's this minus sign that you have to play with, and you pretend it's negative energy, but the interpretation is positive energy. And then they decide, well, it's not negative energy, it's actually going backwards in time. And so the conventional interpretation is that this antimatter is flowing backwards in time. It's not negative energy. But you could play with that minus sign. So, you know, obviously you got to do the experiment, right? And so if they're doing that experiment and they have some results, that's definitely worthwhile to look into.
Yeah, absolutely wonderful.
That OAM thing was mine. David, I really loved the presentation. I couldn't help but notice when you were talking about those wedge dislocations and some of the slides just following, that it looked like the same kind of things that you use as the filters to create OAM, orbital angular momentum for light, to create the twist in the light. It's like a Mobius transformation for spinning or twisting the light. Are you familiar at all with that and see any connections there?
I would guess, I'd have to look into it a little more, but I would guess it's a little bit different. Because here you're literally, well, okay, I mean, you could take the analogy, but I mean, it's literally like you take an apple and you cut a wedge out of it, and then you shear the apple so it's now closed again. So I don't know if that connects to orbital angular momentum, but I'd have to look more into it to really dive into it to see what you mean.
So I have another question also. Sorry, Tim, I'm borrowing Jeremy's computer because I'm at a party at his place. Let's see. So in metric affine gravity, what do you mean specifically by relativistic elasticity?
That's what the Friedrich Hell, that's what he said his goal was when he constructed this metric affine theory of gravity. So he ended up working, he did a postdoc, and he went to this German researcher named Kroner, who was the expert in elasticity theory. And he had some work that was just on relativistic elasticity theory. I mean, he wasn't even saying it was a theory of gravity. He was just saying what happens mathematically if I just take elasticity theory and generalize it to space-time instead of space. And Friedrich Hell was interested in this work, and so he wanted to come in and add the gravitational analog, and a big part of that story was non-metricity. Non-metricity was studied years before Friedrich Hell came out with this theory in 1976, but the thing that Friedrich Hell added was this the hyperstress tensor. It's a 3 tensor that sources matter in a new way, and so he figured out how to source matter in this relativistic elasticity theory interpreted as gravity. But I will also say that metric affine gravity isn't a unique theory either. It's more of a framework. So there's still a lot of freedom and ambiguity in how you basically, you kind of need to add some additional constraints to, because you could write that you basically get general relativity 3 times, so you can mix between the same type of, I mean, maybe it turns out it has different quantum effects too. So I mean, it could turn out that you need all of these terms. You need all 3 of the general relativities and add them together for quantum theory. But I mean, hopefully you don't need that. I don't, you know.
Yeah, hopefully. So by relativistic,
you could have deformations in time, I guess.
So by relativistic elasticity, does he basically mean that there's elasticity or some equivalent of it, but it's still generally covariant and all of that? Is that what he means, roughly speaking?
Yeah, and I mean, just to clarify, I mean, in elasticity theory, you have a 3-dimensional material, right? So it's like you have a solid. And so you're considering a 4-dimensional material. That's the idea.
So
and I mean,
for some context, well, I guess, yeah, if you 4-dimensional.
Yeah, and so it becomes Lorentz covariant because you're going to space-time symmetry, right? Once the material is now in 4 dimensions instead of 3, that preserves the Lorentz covariance.
Okay, so it has to. All right. Yeah. So what we were looking at least in terms of condensed matter physics, is we're kind of going at it a different way. So we don't look at individual defects in space, although they may exist. I would wonder if they're necessarily connected to particles like the dilaton and axion and other things. But what we're looking at in terms of condensed matter physics is we're treating the vacuum itself as a material medium without its own reference frame. And what we mean by that is virtual particles, just like actual particles in glass. There's some plates or something moving around. Is that back?
Sorry, yeah, that's probably.
Oh, no worries. So I'll be quick. So you have your vacuum, and your vacuum has virtual particles popping into and out of existence, and that scales with the amounts of energy density localized there, and also with covariant effects. So 2 observers in different locations can see different material properties in this volume of space-time because of the uncertainty principle. The actual virtual particles that they observe at those different locations, or from their reference frames in this box, will be different. So that gives you covariance from the properties. But then you can treat this as a material medium that just is composed of only virtual particles. And then when you approach it that way, then we're looking to derive the weak and the strong force by saying, okay, so you have a virtual particle. It occupies this volume in space-time according to the time and uncertainty principle in terms of time and energy. So there's some light cones that cut off a region in 4D space-time where this virtual particle exists. Then once there's enough energy density that these virtual particles start to overlap, you get a nonlinearity in electromagnetism that's equivalent to the weak force, and eventually to the strong force as they overlap more and more. It's like a phase change.
But those are linear theories, so. Well, yeah. Oh no, there is nonlinear. No, sorry. No, actually, no. They're non-abelian. There's nonlinearity there.
Yeah. There's you effectively get Yang-Mills plus maybe some other stuff, but we haven't gotten that far into it yet. But what was I saying? Right. So if you look at it from this perspective, then particles are solitonic light. So they're still photons in a sense. So therefore, whatever the background gravity field, any observer is projected onto this curved space-time because they're made of particles that are affected by that refractive index. So an observer made of particles will observe a constant speed of light even in a variable index medium from their perspective as being made of particles. But anyway, when you look at it that way, then it's a refractive index model, which maps to the curvature model that we normally use. But then what you get is some physical insight about how to, I mean, you get basically the physical insight that squeeze states and stuff can manipulate gravity because if you reduce or increase the vacuum noise, then you get a lower or higher speed of light locally. And that's the basic right there.
And so squeeze states, are you squeezing the vacuum itself?
Yeah, squeezed vacuum, normal squeezed light should do the same thing.
And
but you'll have light there too, which is
like non-metricity would allow for squeezing of the vacuum.
Okay, so non-metricity you think is the way to go then?
I'm saying that, yeah, I mean, it sounds like what you're describing could be modeled characterized with non-metricity.
Well, so there needs to be a transform. So basically we're
but
looking at gravity.
It depends on the framework you're working in to some degree, but.
Right, we're looking at gravity as like a lot of people when they like the Dirac equation, they're trying to take the actual wave function and smoothly deform it in some relativistic way, sort of. What we're doing is kind of more like the Born-in field, where you have this vacuum noise, and that vacuum noise corresponds to a refractive index. And then, so if you look at the small scale, you're not going to see the graviton very much. You're just going to see bubbling of all sorts of other particles. But the graviton is defined by some I think there was a Wigner transform over that. And so the noise is in some sense the gravitons. But I mean, that's just kind of what we're looking at. But I'm wondering where that.
Do you have any math?
Yeah, we have a little.
I mean, I'd be down to talk about it later at some point. Yeah, I mean, honestly, it's yeah. I mean, what you're describing is a little complex, so
it's very similar to Professor Tejinder's thing, where you get
you know, if I was just
makes no sense. So
I was just joking in chat here, but it's not a joke. You guys lost me like 20 minutes ago, so I smile and nod. That's my indicator that I'm lost. I'm just like.
Well,
yeah, I mean, we should talk more at another time. I think.
Yeah, I don't have more equations for you right this second, but let's talk more.
Okay.
Yeah, well, I mean, some of what you said might be workable. Some of it maybe not, but yeah, I mean, we can talk more.
Well, yeah, I just I have this idea, and I want to map it to the standard mathematical lingo of the times. Here.
Yeah, and Michael, it's that's wonderful. Yeah, but let's try and it is one, and I appreciate your asking questions, because David's work is so far beyond most people, right? That it's wonderful to have someone who's able to ask intelligent questions, and so so thank you for that. Now, I have
a few more as well.
Well, we'll save
maybe more. Yeah, let's see if anyone else has some.
So I did actually, David, if it's okay, somebody did ask, I'm not sure where it's at, but they wanted to know what you thought on Pei's superforce paper.
Man, I'm trying to remember. I probably looked at it. I don't remember the details of it, but the fact that I don't remember it, I mean, I'm pretty sure I looked at it at some point. Oh man, I don't remember. I don't want to say, so I don't remember exactly.
No,
it wasn't enough where I got super excited, I don't think. So I either didn't understand something or didn't like something is my guess, but I don't know for sure. I probably should look into it in more detail, to be honest.
Yeah, no, that's totally fine. I appreciate you taking that one. Well, I think in terms of questions, I mean, those were probably all the big ones. And I put a bunch up on the screen, but it gets so technical, and my screen keeps scrolling, so I'm losing them all.
One quick question, very quick. Where might we search for axions and dilitons if they're added in this model?
Well, I mean, the problem is that it depends on more details. Like if you look into the literature for axions, it's a huge mess. There's not a consensus whatsoever on how to do that. There's like hundreds of ideas probably. So, in my opinion, I think exploring spontaneous symmetry breaking of gravity is the way to go, because it just makes a lot of sense that conformal gravity as a gauge theory might have nice quantum gravity properties, and there's no reason why you can't study it like the other forces, like a quantum field theory. And so and we know the Higgs mechanism gives mass to other particles, and there's work that's been done by the string theorists that's explored the first math for doing spontaneous symmetry breaking of gravity, but they haven't connected it to physically realistic theories. So in my opinion, I would go for the axion and dilaton as coming from spontaneous symmetry breaking for gravity, but I haven't worked that out yet.
Cool. And
Wonderful.
just briefly,
Well-
just sorry, just to follow up to that. I mean, we might as well, anyway, it's only ever so once in a while we get to talk to David. Now, so the Hagen-Kleiner.
But that's why it's only once in a while, because Michael jumps in with the questions.
So
David's exhausted. I won't see him for another 6 months after this. So
It's all good. I'm doing good right now.
So how might they? How might these the axion and the dilaton relate to gravitational memory, or is that in a different?
I don't know. Gravitational memory. I mean, I'd have to think more about hysteresis and gravity and what that would even mean.
I think that was something that. What was the name?
There's this other gravitational memory stuff with gravitational waves.
Yeah, the infrared triangle. They had the soft particles, infrared limit, and then there was the gravitational memory concept. Yeah, that.
There is torsion can help clean up some stuff in the IR for QED, but it hasn't really. It's hard to say. Yeah, it's hard to say. It's complicated.
yeah. Well, yeah.
We'll talk about it another time then.
Yeah, and Michael, thank you. Let me bring in. I'm going to bring in Drew and Brian. Everybody, again, one more giant applause for Dr. David Chester. David, thank you. You just
Thanks for having me.
absolutely brilliant. And again, I know it sounds like I'm brown nosing, but you are one of those physicists who is going to change the world. You already are. So that's. I know I'm brown nosing, but trust me, history will prove me right on that. So, well, guys, why don't we move along to lab time? Why don't I start? If it's okay, I'll start with Mark, and then I'll go to Brian, and then maybe Drew after that, if we switch things up a little bit. But if that works.
I was hoping that Todd would be here. Todd's going to be joining in a moment. Is Jack Sarfatti joining today?
Jack is not. No, so Jack is traveling. He's in London. He was over the last week. He had some unexpected scheduling stuff come up, and what he said was he was going to try and make it in, but it looks like he's not going to be able to join us. He might be able to pop in later. I did email him. I've texted him and stuff like that, but he is in London, and so his schedule is different, and so it is unfortunate, but what I can do, actually, I'll put some links into the Cortona conference in the YouTube notes here. And so people can watch that at another time, and we will try and get Jack back on. As all of you guys know, he does make cameo appearances at APEC. So, we can hopefully have some cameos with him as well.
Okay. So what we have going on today is this was a recommendation from Todd Diciato to try a replication of I wouldn't really call this the Alciphon experiment, but it does require all the equipment that we already had set up. So I'm just going to go ahead and give you a short synopsis of what we're doing. So the magnetic field in this experiment has been configured differently because we have two separate electromagnets. We're actually able to change the polarity on one of them, so that when the magnetic field is turned on, the field in the center actually gets canceled out. And Todd believes that as the field strength increases, any sample, any paramagnetic or non-magnetic material that would be inside that field would gain weight and hence prove his theory. I can't speak on his behalf exactly why that is the case, but we're going to give that a shot over here. So we have on on my right, it might be your left. This number is the 1.4859 grams. That's a sample that's sitting inside the chamber. Small piece of aluminum. This is just set up already from a previous test. The force gauge over here, 1.65 newtons. That's the weight of the entire copper chamber in there. Now, we're not going to be pumping any RF into this, so if we do see a weight gain, we'll be seeing it both on the force meter and on the weight of the sample itself. Now, the potential on the bottom, 1.338 millivolts, that's the current running through it right now. It should really read 0 because the electromagnet is not turned on. But I'm going to go ahead and get this started in just one moment. Let me set the settings correctly so we can have this run through pretty quickly. Okay, there we go. I'll start by turning on the power supply. And upload. Okay, so now I'm controlling the power supply via the Arduino system. I probably don't have something connected properly here with the potential. I'm just going to remove that for now from the equation because that is not correct. Okay, so the current is rising. It's around 10 amps. It's going up toward 15. We're not seeing any changes right now. I do have to apologize. I do not understand exactly why this experiment is supposed to do anything. Oh, there is maybe a small blip there. Hopefully, if Todd can get on, he'll be able to explain exactly why this will prove anything. But in the center of the chamber right now, we should be seeing roughly no Gauss, almost no magnetic field. On the edges of the plates, we should see a magnetic field of about half a Tesla right now. We're coming up on around 20 amps going into the electromagnet. Now, the weight of the copper chambers does seem to be fluctuating, but I'm not seeing much of a weight gain or weight loss in any of this. Todd, if you're there, you can maybe comment in the chat and explain to everyone what it is exactly we're seeing. He asked me to run this, so I'll be running it. Weight does seem to be changing quite rapidly, actually. And we're coming up to like the max weight loss right now. The max current, that is. So we're about 30 amps right now, and that's the peak of what the magnetic field can output. So I guess we'll call this one a dud, unless I did something wrong. Todd will have to get back to me on that. I'll just shut this off for now. Okay, some other things that we are doing here at the lab. For anyone who's seen our last presentation on APEC back in July, we showed you some interesting effect that happens with superconductors as they warmed up in a specific magnetic field configuration. It would rise toward the magnet. Now, we've been looking at this effect extensively, trying many different magnetic fields, and Michael Perrone has actually done some background research looking for other papers that talk about it. And it turns out it is a unique effect. We're going to be writing a scientific paper on it, and we are studying it on a much deeper level here at the lab, trying to get some quantitative data instead of just qualitative data in order to actually write a paper. And we have some PhDs involved in that as well. And so that's something that's pretty exciting that's going on here as well. Another thing that we've been working on is the EPR machine back there from George Hathaway. We did get that to run. We were able to get an EPR spectra, but are having trouble using the stylus system. Has wires on it. I mean, like physical wires that move the pen around. And there's an issue with the slack in the system, and we just couldn't seem to fix it. But we did manage to get an EPR spectra on that machine for DPPH. An EPR spectra, by the way, for those who don't know, that would be on the x-axis. You're looking at magnetic field strength change. On the y-axis, you're looking at the absorption of RF. So in order to see electron paramagnetic resonance, you have to get right in the right frequency, and then the sample is sitting inside of a chamber that's finely tuned, and the RF starts to get absorbed into the sample, and then it rejects the RF, and then it goes back and forth. And those are the squiggles on the lines that you see in EPR spectra. If you were to Google EPR spectra right now, you'd see squiggly lines that represent the RF absorption over a course of magnetic field strength. So we did manage to get that going. We're trying to convert the setup over here. This is our custom-made EPR setup, which is looking at dynamic nuclear orientation for potential weight loss. So we're going to be using LabVIEW to try and take the data coming out of these various systems and convert it into those squiggly lines as well, so that we can see those EPR spectra as alongside the weight of the samples as it's going through it. If anyone watching this knows how to use LabVIEW or can program LabVIEW, we do have a small budget for that. We are looking for somebody who can join us on a Zoom call or come down here in person to help out with that. It's been pretty tricky to figure that part out. So you can just reach out, mark@falconspace.org, or you can put something in the comments right now, and we'll be sure to reach out to you or reach out to us.
Awesome. Mark, thank you so much. So while you were giving that demo, I dropped a couple of links in chat. Again, falconspace.org. That is Mark's new website. I also dropped a chat in for Linktree. That's the Linktree for Falcon Space. That will give you all of his links. That way you can reach out to him directly through the web form. There are lots of ways to get in touch. Mark has been, just as a reminder, Mark is a founder of this conference. He has been doing these experiments for years. We have gone through experiment after experiment after experiment. He is working on absolutely remarkable stuff. He had stuff in the lab the other day that is brand new. He's not ready to share yet. So absolutely remarkable work and results. Mark, thank you so much.
Just one moment. Todd Desiato in the chat, he just mentioned that we're doing something wrong here. He said the sample should be above the center line of the magnet. So
okay, let me take myself back out.
No, this is going to take a couple of minutes, so we might as well have somebody else present. I'm going to run back there and try to reconfigure it.
Okay. Well, why don't we do that? So why don't I go to Brian St. Clair next? And so, as Jeremy Rys should say, please carefully and methodically depress the like button and strongly consider subscribing to our channel. Right. So the Alt Propulsion channel on YouTube, that's the one that I'm hoping you subscribe to. Take a look at the altpropulsion.com website. Share it with a friend, share it with a few friends. Basically, just help us grow our reminder list. That is a big thing for us. And that way, if you miss a conference, you at least know about it, right? The nice thing about using StreamYard is the same link that you use for the live show becomes the link that goes to the replay. So if you miss the conference, you can see it just by clicking on the link in email. The open mic sessions are a little bit different. StreamYard is again, it's very advantageous for webinars. Zoom still has a few advantages in terms of a flat open discussion forum. So right now we're kind of juggling both, but let me go and bring in Mr. Brian St. Clair. Brian, thank you, sir. It is wonderful to have you back here. You have an update for us, I believe.
I do. I've got a little bit of an update. We've been still working on the Trammel engine. Most of you know who I am and what we were doing with the pi and the purely mechanical propulsion systems, closed loop, entirely closed loop. We're progressed to the point with the Trammel version 1, or the V1 if you want to call it. We can get approximately 10 pounds of static force from the engine, thrust. We're right at the limit of what the internals on that engine will do. If we crank it a little bit higher, I know very well that it's just going to grenade. So right now we're working on version 2, which is behind me. I covered up part of it just because some of the internals are still proprietary. We do have a fresh video, or fairly fresh video on YouTube. You can check that out. Just seeing the discs and the top pieces and how they interact. I know a lot of people don't necessarily agree with what we claim that we're doing, but again, I make no claims. We're not here to prove anything. We just are here to demonstrate what we know how to do, and we move on from that. We know that we've discovered a number of things that we didn't know about the machine before. Mike Marsden, of course, was the inventor of the Mach 1 back in 2010, 2011 era. He didn't tell all of the secrets, obviously, and the few people that did get close enough to him to understand at least part of the system they were still never looped in on the entire internal component part of that system. I do still get a lot of people that will say no, that's not possible. You've got to have magnetic fields, you've got to have quantum fields, you've got to have some sort of output. It's got to grab something and pull itself along. All you've really got to do is think about a couple of quick things. Number one, if think about the fact that if you were to create a very small explosion and do that, 5,000 times a minute, you would think that you would have something that would be reasonably uncontrollable. But we have that every time we jump in our car and drive down the highway. The cylinders inside the engine are micro explosions every time they light off and produce power. When you think about, we can't get more torque out of it than what we're putting in as far as actual torque. I'm not talking about energy. I'm not talking about the electricity. But think about the guys working on the side of the road and they're using jackhammers. Those guys are holding on to those with their hands and they're breaking thousands of tons of concrete every minute with those things. It's incredibly possible. It's just that we have not been taught the right way of thinking about it. And that's what's really taken a long time to really make the system usable. So anyway, behind me, I do have the version 2, the Trammel. I did have to cover up part of it, honestly. I just can't show it just yet. It does turn, it does move, but there are some pieces inside that aren't set up just right yet. So I would love to crank it up a little bit faster for you, but I just can't do that right now. We have found a number of things that we were suspecting that I'm glad to share. Number one is that the actual thrust force will be coming from the center disk. That's where we believe that 99% of the thrust is actually going to be generated. And so therefore we need a bearing support directly above that, because this is set to move in the upward position or upward direction. I'm planning tentatively. I haven't really talked to Ross yet. Ross Small works with me on a lot of this stuff. I haven't really talked to him about it yet, but I'm kind of tentatively planning on putting together a short presentation on how we believe this is working. And I would really, really hope that the version 2 is going to be at least demonstratable by the time we have that presentation ready for APEC. But that's really about it. Like I told Tim earlier, I've only got a really short presentation. It's not really a presentation. It's just an update. We're working at it. It's coming along. This aluminum unit, the whole thing weighs about what a couple of the discs inside the original unit weighed. So we're in really good shape, weight to power ratio wise, and we're just looking forward to being able to demonstrate how this thing works. That's about all I've got.
Brian, thank you. Thank you so much. Thank you
You're
so
welcome.
much. Well, and updates are awesome. It doesn't always have to be a demo. Just don't be a stranger. Come back anytime and update us on how things are going, the work that you're doing. I mean, your work is heavy duty, industrial grade. You're putting in the effort and you're getting the results with it. So it's absolutely wonderful to have you here. We should probably drop your website in there. It's the St. Clair Tech website, right?
Yep, it's stclairtech.tech. It's an open website. Everything is perusable. There are links to the blog where I went into great detail about the pi system. I haven't gone into great detail about the Trammel for obvious reasons. There are also links to, I believe there's a link to APEC. There's a link to our our YouTube channel, and a few other things in there, and a couple of videos and a couple of embedded cool things. So go ahead and check that out anytime. I appreciate it.
Yeah, and I just put that in under your name. So it's stclairtech.tech.
Yes.
And people should definitely check that out and stay updated because you are actively working. And then you're still collaborating with Ross Small also, right?
Correct. I just was talking with Ross just before the presentation, and he's on. He's watching. I know he had a lot of other things going on today. It's been a really busy summer. Unfortunately, I would have liked to have been on sooner than this, but this was really the first time I've had a chance to break free and do this.
Well, you know what? Thank you for coming on. Though it is wonderful to see you again. You look healthy. You look happy. You look like things are moving forward. Everything is good. Everything is good. Okay.
Absolutely.
Well, Brian, thank you again. Let me. So what I'm going to do now is I want to go to Drew in sunny Florida. And oh, you know what? Okay, here I will not go to Drew quite yet. Drew is on another line. Let me go to Jared. Jared is waving. Mr. Jared Yates, who I've worked closely with, and Jared has had an enormous summer as well. He flew out and you did the UFO research this summer, and then you're also building stuff, right? You're working on the Graviflyer, and you have a couple other projects.
Yep. So the thing that I wanted to share is just last night, I got a really interesting result with the Graviflyer that lines up with what the inventor, Alexei, said that we should be doing. So for those of you not familiar with the Graviflyer, looks kind of like a flying saucer. You got a spinning disc on the bottom. It's got magnets on it. You got a spinning disc on the top that doesn't have any magnets. The bottom disc is charged really high with negative voltage. The top disc is charged really high with positive voltage. And then you apply an RF signal to the center disc. So I have a ham radio set up here that I'm using to dial in the frequencies just right. And what the inventor said was that this thing is supposed to operate better during the daytime than the nighttime because he thinks it's related to ionospheric conditions. So yesterday I did some tests sweeping through different frequencies in the middle of the day when the ionosphere was at its most highly charged. And then at the end of the day, when the ionosphere was really quiet. And the differences were quite astonishing. So during the daytime, at one specific frequency range, I was able to get the bottom spinning disc, I call it a rotor. I got the bottom rotor to speed up and the top rotor to slow down. And then at a higher frequency, I got the inverse to happen. The bottom rotor slowed down and the top one sped up. And then I did the experiment again at nighttime, and it completely changed everything. The bottom disc didn't really change at all, but the top disc, it changed a ton. So I think it has to do with the charge dispersion. When you are emitting the RF from that mid plate, you're creating a circuit up to the ionosphere, and that circuit is allowing for some level of charge dispersion of all of those electrons stacking up on the bottom disk, or all those holes stacking up on the top disk. When you connect to the ionosphere and complete that circuit, you're going to have some kind of interactions between the ionosphere and the other half of the circuit, the graviflyer. So that was my super awesome results, was that I got it to, and the best part. So last night, I tried offsetting the speed of this thing so that when I would apply the RF and it would speed up to match the speed of the other disk. So the crazy thing was, when I released the RF, it didn't slow back down like it had in every other iteration that I'd done. I released my gun, I waited about 10 seconds, and that disk stayed at the higher speed rather than slowing back down like it should have. So that's the weird thing. That's the latest. I got to figure out what's going on now. And it's super exciting, especially because it totally tracks with what the inventor claimed you should be seeing.
Okay, awesome. Sorry about that, Jared. I hit the wrong button there. Too much going on. Jared, thank you so much. Thank you so much. Jared is, man, you are just working so hard continuously, getting so many results. And then you are working actually with Charlie. So the graviflyer thing is not that for you. That's not in, I was going to say in a vacuum. That would be a pun, but
we have a whole team. It's Charles and Mike Gamble and myself. The three of us have been working together on this for the better part of a year now. And we're really starting to make some good headway. We're really excited.
Yeah, absolutely amazing. Absolutely amazing. Okay, well, Jared, let me thank you yet again, sir. Now I'm going to go back to Drew in sunny Florida. Drew, are you with us, sir? Okay, and you're muted. If I can ask you to, let me see.
Yeah, I'm here.
There we go. There, yeah. Drew, thank you for popping in. Thank you very much. Let me take myself out, and any updates that you want to give, go for it, sir.
Yeah. Can y'all hear me?
Yeah. No, we can hear you fine. And then if you want to do a screen share, again, it's the present button. And you can share screen, you can upload, if you wanted to upload a PowerPoint or something like that, anything, just let me know what you need, and I'm happy to help
Hearing
out.
like 3 different versions of the sound, so something's very, very wrong.
Let me see. I'm going to mute out Mark, and I'll mute myself, and that should solve it. Okay, it looks like we lost Drew. So Drew may be back in just a moment. You know what? The only person remaining is Bernie. Let me put Bernie on. Bernie!
I'm here. How's it going?
Hey, thanks for popping in.
Absolutely.
What are you working on?
Epic presentation so far. I've been putting together my alchemy stuff tied in with what I've done with silver in electrolysis and tying it to the moon cycles, as well as these metamaterials back to Jeremy's presentation, and that I've produced some clear aluminum. And then I've been contacted by another fellow that's been following my work that's sent me pictures of clear, transparent silver that he's made. And we're going to be doing an interview together on that in the next week or two. But sadly, I did not have it together for today yet. But quite stoked on that, because it's like clear silver. Like, has anybody seen that? But I've got pictures of it where it's literally the 1 ounce and 10 ounce silver bars, and they're completely transparent, that this man, I believe Mike, has done. And yeah, it's very, very fascinating stuff. Give me one moment and I can connect my other camera here and show some of the clear aluminum material that I've made as well as some of the monoatomic stuff. I'll get a little presentation ready, but it looks like Drew's back, so I'll hand it over to him while I set up here.
Awesome. Bernie, thank you. And I just dropped both of your channels in there. If you haven't subscribed to Bernie's channel, please, again, carefully and methodically depress the subscribe button. So Drew, how are you doing, sir? Let me unmute you again. Okay. Sorry, sir. You are still muted. You haven't. Okay. It could be, you know what?
I'm
Drew,
hearing three versions of everything from everybody today.
you may have different speakers. Maybe you have multiple speakers. I can mute myself out, and then the only person speaking will be you.
Drew sounded fine to me from what I heard when
He does. I think he's getting feedback from multiple speakers. Why don't I do that, Drew? I'll mute myself out, and if you want, you might be able to turn your volume down. But yeah, you sound fine to me if you want to.
Okay, I don't know what's going on. I'm just going to give an update as to where I am, and maybe somebody will hear it. It's been a really strange day.
Yeah, no, you sound great.
Anyhow,
You sound great.
This is the latest version of the propulsion system. We're down to what you see here, and basically it's operating at about 40% thrust to weight ratio, and it's just working on stacking. I have a thing you should not do. You should never, if you're doing vapor deposition, you should never let your little copper puck make it all the way through, burn through. See how it's burned all the way through? Never burn through your copper puck, because then it burns through your vapor deposition housing and into your neodymium magnets, and you end up depositing neodymium magnet all over your chamber. And all
Okay. And you still, again, Drew, you sound great. I know it can be a challenge when you've got voices coming back at you from yourself. That can be really difficult. So, okay. Well, let me thank you. Thank you very much. And again, internet stuff, sometimes it just gets us all, but thank you very, very much. And so for, I guess, 40% thrust, that's up from about 30%. I think you were at 30%. So those are giant gains. Congratulations, man. Congratulations. Okay. Well, Drew, let me take you out for a moment. And okay. So I think that's it in terms of lab updates. So I'll tell you what, guys, why don't I do this? I'm going to throw the room up. We have a couple more spots here. I can bring Bernie back in. I think Mark had more, Bernie had more. And what I'm going to do is drop a link in chat. I'm actually looking for that. There we go. So I'm just going to drop this right into chat. If you guys want to come into the studio, if anybody has anything to share, that is our studio link. So hop on in if you have updates to share with the APEC group. And again, I think Mark has more, Bernie has more. So why don't I do this? I think right now I'm just going to bring everybody on stage here, as they say, and let me see. Michael Perone is not there. So we've got, this is everybody that we have in the studio right now. We may have some more. I had a couple folks that were asking about trying to do ad hoc presentations. If you're watching, that link is in there. If you want to come on, we've got, we've only been going about 3 hours here, so we have more time. Looks like Mark is back. Mark, if you have updates for us. And then I think Bernie had some more that he's actually working on. So
yeah, looks like I'm running into some computer problem here, trying to get it all up. Okay, it's cleaning up a bit. I'm just trying to get the camera to turn back on. Just a couple more minutes.
Okay. Yeah, well, I'll tell you what, guys. While we're waiting, I could kind of walk you through some of the stuff that we're doing. So let me do that. Here we go. Okay. So I will start out with. I'll start out this. So that's our website. Sorry. So again, the APEC website, if you haven't gone there lately, latest conference events, today's show, scroll down. I'm going to be making some updates to this thing in the near future. What I would ask is, if you haven't registered yet for the email list, that join APEC button, and it's free, it's secure, there's no cost, no security risk, anything like that. This is our private secure MailChimp email list. We do updates for APEC with this. Okay, so what I want to do now I'll show you some of the new stuff that we've been working on. So falconspace.org. I am very proud to show you all the Falcon Space website. This is for Mark Sokol's research effort. You can see we went with kind of some darker themes there, and it's kind of art focused for the time being. So this just provides an overview of everything that Falcon Space is involved with. I do want to show you, and I think you can see this. Turn the volume down. So we do have a full presentation. This is from an older APEC from Mark. Mark also has an interview with David Alzafon that we're going to be putting up soon, and I'm really excited about that. And the other thing that we've added is a very nice photo gallery for some of the highlights. So we've got that. We will put some other videos in. It's just got team info and the contact us. So we've got that one. The other website, I will show you mine very quickly. And I believe, yeah, you can see that. So again, I'm Tim Ventura. I am the APEC moderator. This website, I have some info about the conference there. I also have a podcast. So I guess the notable thing for me is I do an interview channel, and I just rolled out an audio format. These are actually links. So if you listen to podcasts, any of the interviews that I do, you can see those in podcast format. I'll show you the YouTube channel in a moment. And so these are my interviews. Again, if you want to subscribe, Lord knows I could use the subscribers. I am not focused completely on propulsion. This is a passion project, so I do different stuff. Yesterday, I did one. It's not getting the views that it should. Emil Grafstra did an amazing discussion of Neuralink and brain implants. But I've also done a lot on first contact, UAPs. You can see Jack Sarfatti up there. In fact, I have done interviews with pretty much everybody, interviews or presentations with pretty much everybody who's on this panel now. So that is my website. Again, the alienscientist.com, Jeremy Rys. This is something that they are doing amazing work. Jeremy has been doing amazing work. And just as a reminder for everybody, he was on YouTube in the beginning, and he has been just powering through this stuff ever since. So alienscientist.com. And let me see, I'm trying to think of anything else that might be out there. Oh, you know what? I want to show you Michael Perrone's website as well. So Michael Perrone, he did a lot of work on the LK99 superconductor. He is also doing a lot of other material science work, and he has a website up at sanrel.com. So this is kind of some of the latest stuff that we have going on. There's definitely a lot more out there. You know what? I don't think you can see that. Sorry. Let me put Sanrel. There we go. Now you should be able to see. So that is Sanrel. This is Michael Perrone's website. Okay. And then Alien Scientist, because I bet that one got missed as well. Sorry. StreamYard is kind of goes by the tab. And so if you open a new tab, it won't always show it. So I would definitely recommend taking a look at all of those all of those websites, and again, we have multiple channels here. We have the alt propulsion channel, alien scientist channel. Bernie has 2 channels. We drop links into chat for those. So that's kind of what I've got there. And we had just a couple of more people come in here. Mike Doss came in, and Curtis Horn came in, and Jeremiah Pop. Okay, and I think our studio is pretty much full once we add these gentlemen in. And let me see. Can we fit them all in there? There we go. That's the whole crew. Okay. And it looks like Drew, let me see. I'll and that's Jeremiah. So Jeremiah, you were here. Jeremiah the engineer. You don't have to do chat. You can talk now, man. Go for it.
I missed the first probably 50 minutes of Jeremy's presentation, and what I just jumped into it as I was heading back in the door. I'm like, oh, this was juicy, man. But of course, there's no time or gap to stop between then and the end, so I've got to go back to the beginning after this is all over and take a look at what he was talking about. But it was definitely on par, and I wanted to thank you again personally for getting Brian Kelly on. He really nailed that presentation as far as the raw simplicity of his idea, what he's presenting. And Wayne and I have both talked to him privately, and as far as what he's presenting about a basic absorption of photonic energy and the temporary storage in the physical structure of the matter of that photonic energy, because you're increasing the local mass energy density, then you're changing or decreasing the gravitational coupling coefficient because you just recoupled with something else. And so it's a really straightforward thing. Hydrogen absorbs photons really well. That's his idea, is link hydrogen with graphene. Use this graphene material. It's the simplest, most basic metamaterial that you could possibly want to test this stuff with, and then hit it with the right wavelength of light. That was basically all I was saying, is take graphene, hit it with the right wavelength of light, and then watch its inertia and its mass drop down. Simple as that. So nobody has tried it in any kind of serious order so far as we've seen, but that's big reason is graphene very hard to make, and also not available to purchase right off the shelf commercially as far as I've been able to find. So,
and Brian is actually saying thanks in chat, and we have a couple of people that are trying to enter the studio room, but we're currently full. We are full unless we upgrade. But if we upgrade, I'm not sure what it's going to handle like, and I don't think I can do that in the middle of a conference. So we may have to come back to that in between.
Tim, if you're ready, the experiment here is ready to go.
Yeah. Okay. Well, let me do this. Let me take everybody out. I will make. Is there a way to make Mark the presenter? Yes. Solo layout. There we go.
Okay. So I was conferring with Todd, who is predisposed at the moment. He said, get rid of the copper chamber and go with a heavier sample. Also put the sample on the top of the canceled out magnetic field and try it again. So now we have a lead weight, weighs about 77.28 grams. I'm hearing some background noise. Everyone mute themselves. Tim, is that you?
No, but I just muted everybody out, so you should be good, Mark. Sorry about that.
Okay, so the sample is a lead weight. It's hanging on top of the magnetic field, where the magnetic field will be canceled out, and it weighs 77 grams, which is roughly about 2.5, more like 3 ounces of lead there. Now, the magnetic field meter that you see over there that shows 48 Gauss, it will not read 0. That's because it is measuring the magnetic field from the side, and the magnetic field will only be canceled out in the center. So you will see it rising as the magnetic field strength increases, and that will give you a gauge of how strong our field is. I'm going to upload the file right now to our Arduino to control the electromagnet, and it should start running momentarily. Let's see. Yeah, there it goes. Okay, so magnetic field is starting. Oh, we are seeing close to drop to near 0 there. This force gauge can actually, we can get rid of this because this is not related to this experiment at the moment. Only thing that is relevant is the weight of this thing, our lead weight. The magnetic field is rising. We're at about 13, 15 amps right now. Normally, if the magnetic fields were both aligned with each other, at this point, we'd be roughly at around 3,000 to 4,000 Gauss, or 0.3, 0.4 Tesla. Okay, we're coming up at 15 amps right now. We're doing a quick scan through the magnetic field strength. You can see on the Gauss meter, it's slowly rising. That's just to give you an idea what's going on. And it looks like the lead sample weight is hardly changing at all. We're at 25 amps right now. So this is close to the limit of what the power supply can provide. I believe it goes up to about 30 amps. Well, we're not really seeing anything, so I guess this hypothesis has been proven wrong. Unless Todd has anything else to add to it. Again, these are two fields on either side that are canceling each other out, which is similar to the Boyd-Bushman effect, where we've seen two magnets that are in opposition with each other would fall slower than the speed of gravity. In this experiment, we're checking what would happen to a lead weight hanging inside such a field, such a canceled out magnetic field.
So the meter on the bottom there, then let me ask, is that measuring your magnetic flux between those two?
Not between them. You see the piece of copper tape. It's actually measuring it on the right side of the magnet. So that's why it's not zero.
So you did field reverse the coil then? You did field reverse. Yes. So are you norths in the center or souths in the center?
I'm not certain of that. I just switched out one wire. I don't know if it would make a difference.
It would. It shouldn't. It should not theoretically make a difference, because if you broke into the thing around, but I don't know. I'm just curious because I know that some people claim canceling the souths in the center seems to, for some reason, make a difference. They claim in their experiments. So I don't know how much factor is to that, but something to consider anyways.
Right, and Jeremiah, you did an experiment with the Boyd-Bushman force beamer that was with more magnets, right? It was like 6
North
magnets.
is strongest.
Yeah, 5 magnets in total. There was the 4 periphery magnets, all each arranged at 90 degrees to each other along the same plane and canceling at the center point. And there was the 5th magnet, which was removable, and that 5th magnet I replaced with a field control coil. But I hadn't actually seen what Bushman's beamer looked like up until that point. I just seen the pictures in his patent, and after seeing what he actually did, which is quite a lot different than what he put in his patents, I can see why he was able to pump the impedance of his system, where I was having major impedance matching problems.
Yeah, and it's so what I'm trying to do, and again, our studio is just about full. What it's saying is it's not going to let me upgrade without contacting our team owner. I think that's Jeremy Rys. So that's something that we can kind of work on. I am trying to get Don Tadaya in to give us an update on his UAP work as well. So let me see. I think that we have space. So Don, if you're listening, he said he's just getting settled in. I'm going to try and get him in the studio. We haven't had Don here in quite a while. So
give me about 30 seconds here and I should be ready to show off a few things.
okay. And let me see. So we have folks who are trying to kind of come in, and it's getting a little packed up, but we'll see if Don can make it work.
If you guys are interested in some circuitry, I got something.
Okay, so it looks like Drew is back. Okay, so I'm going to message John and just say, Don, let me know when you're ready.
Are you still hearing an echo from everybody 3 times, Drew? or is it much better now?
No, it turned out that that this, whatever this is,
Drew, do you want to do another update on your stuff? Do you want to do more in depth on what you're doing?
Yeah, I really liked what you'd shown before. I mean, that was definitely some high-edge stuff. It looked like you were using Kapton as your dielectric or a polyimide film, and I'm guessing because the vapor deposition stuff that you've been working on, you're probably using that for your electrodes.
Oh, okay. You know what? Okay, if it's okay, so I'm gonna. Does anybody want to volunteer to step out of the conference for just a moment? The person I would remove is Jeremy, but it's not letting me. I think because he's a team leader here. So, can anybody bail for a bit so I can bring Dawn in?
I can step out for a little bit and then come back in and do my presentation soon.
We just bailed on your behalf, so thank you.
Okay. There's Dawn. Okay. Let me bring Dawn in.
What's up, guys? Hello, everybody.
Dawn, thank you. It's a full house today. It is a full house.
I know.
It's like a 7-Eleven. It's too much good stuff, you know.
So you guys aren't letting me in. You guys are full house.
John, you still got a minute, like to wait? Because I'm just curious. I'm curious to hear Drew's response.
Please, no. I do. I'm not in any rush at all.
Before you get going.
Okay. Well, yeah. Let me do this then.
So.
I'm here to listen to you guys first. I just want some feedback. That's all.
Yeah. Let me here. I'm gonna do solo layout for Drew. Drew, update us, sir. Go for it.
All right. Well, again, this is the latest configuration of the impulse thruster. Imagine stacking several thousand of these on top of each other and powering them with the energy from literally your cell phone. I'm up to about 40% thrust to weight ratio, and stacking is a challenge, but it's going well. The test is going well. Kind of getting into some physical chemistry now, trying to optimize what I call meta surfaces, because I'm actually vapor depositing several layers of material to try and enhance certain properties.
Hot damn.
So I don't really know exactly what a metamaterial definition is. So I think anything that's exotic and does something that it isn't expecting to do because you alter the surface is a metamaterial. So that's what I am.
Metamaterials are defined as any material exhibiting properties that it wouldn't possess in nature. So it's a synthesized version of a material or a refined version or a geometric structure of material not found in nature that exhibits unusual properties.
Okay, well then that's my version of a metamaterial, and right now I am just trying to optimize it for charge enhancement, trying to pack as much charge into it as possible.
And Drew, if it's okay, I want to drop a copy of your patent into chat, if that's okay.
Sure.
Yeah, there we go.
Yeah, there's been a whole bunch of updates. We just filed a whole bunch more stuff. That's why I'm able to show you this, because we just filed a whole bunch of stuff for flat plate theory.
Yeah, and so you guys have a patented system. This is something that
I'd love to see your new patents too, and the any new papers that you file. I'd definitely like to take a look at those. And
should be the last. We did a filing about 6 months ago, 5 months ago, and it's out there now. You can go out to the patent and read about the stuff from about 5 months ago, and then we just filed last week or the week before a whole bunch more stuff. But
I've seen your other patent. I've seen the one that looks exactly like the Forge's patent, but with an updated layering of materials. And you've got different densities of K dielectrics and masses and stuff in there, which I thought was like, this is a pretty good idea. You're trying to create a gradient. You're trying to control the gradient geometry and the charging time, the way that it transits through three-dimensional space around that.
It's all about electrostatic pressure. If you've got a material and you have a low electrostatic pressure on this side and high electrostatic pressure on this side, then the universe is going to push the thing that way. Just the way it works. But we've discovered that there's not a whole lot of universe between this side of the film and this side of the film. So we're only operating on the universe's pressure from inside the film. The universe is actually pushing on the film this way, and it's pushing on the film this way. and we've pretty much zeroed this side, so the universe doesn't have a chance to push on this side. When it comes in from the outside here, that's equal to this. So the universe pushing this way and the universe pushing this way are pretty much the same. It's the universe that's inside, you know, between.
Oh yeah,
between
it's a tiny little space. That's why you make them thin. That's why you stack them up.
And yeah, and we figured out that a way to optimize the metal to plastic interface, the metal to polymer interface, so that the universe exchanges far more momentum. So let's just say this is the metal surface out here, and this is the polymer surface right here. The universe is going, you know, ping, 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 and it's exchanging momentum on a, I guess, on a Planck scale. That's my guess. So we're literally stealing momentum from the universe. And someday I'm sure God's going to ask for it back, but I'm not going to be around to worry about it. So we've optimized the interface between the metal and the polymer so that all of those little trillions and trillions and trillions and trillions and trillions of interactions actually add up to force. And the force they add up to now is about 40% of the weight of the plastic.
Is that any directional, or is that specifically away from gravity?
That is omnidirectional. It has nothing to do with gravity.
Okay.
Although it does work against gravity. I mean, you can.
That's okay. I get that. It just you tested it at different angles and found that there was absolutely no difference in the force vectors.
Not at all.
Okay, well that's awesome. That's a pure isolated thrust, and that follows in line with Mike McCulloch's idea of the information horizon. And so I'm sure you're familiar with this. Mike McCulloch uses polyimide film in his thrusters and heats that film up to an increased temperature, somewhere around 50 to 55 degrees maximum Celsius. And at that point, it's a leaky dielectric, so electrons from the cathode side will accelerate, especially if the cathode is a rough surface or happens to be like a carbon nanotube forest or something, and they'll accelerate through the polyimide film and tunnel their way through and strike the anode. And when they do, depending on the velocity that they reached in that tiny little gap of maybe 6 to 12 micrometers, they will have accelerated to near relativistic velocities because of the incredible electric field between those 2 points. Figure about, 4 kV, 2 to 4 kV across 12 micrometers is quite an electric field. So when they do, they create an information horizon which can create a unidirectional thrust. Depending if you place a mass on one side of the thruster or the other, you'll either destroy the thrust or you can enhance it. So it's a very interesting phenomenon. It has to do with the electric field transmitted by the electron in motion just during its tiny little transit. Extremely short.
Yeah, I don't think that's right. I mean, I have a real good guess as to what's happening there, and I think he'll find that if he flips the polarity of the field, he's going to get the thrust in the same direction.
Well, I mean, he has made them symmetrically and measures thrust opposing. It depends which side the cathode and the anode is on. So if it's a completely symmetrical thruster, it'll still generate a unidirectional thrust.
Ours, the polarity of the field doesn't make any difference because
it's really just electrostatic pressure no matter what, hey?
It's really just electrostatic pressure. So
that's incredible.
In his case, he's probably generating an asymmetry just from the direction of the current flow.
It could be. Like in your system, though, if it doesn't matter which polarity, then that either means it's the materials that give it a polarization, or it's the mass on one side versus the other.
Yeah, it's not so much the mass; it's the difference in materials.
I'm just curious. Are you using carbon as one of your plates for the internal coating?
No.
Oh, it's all metals. All metals.
Well, it's all polymer.
Well, I mean, yeah, you've got a polymer between the two, but wait, so it's not just one polymer in between? That's your dielectric?
Nope, it's a couple of them.
So there it is. So you're generating the gradient just like it shows in your patent with them all.
That's exactly. That's the only way this works is if you generate a gradient, and in order to generate a gradient, you got to have two different materials for the field to pass through.
And that's why you're using the parallel plate system, because you can generate a flat plate gradient.
Yeah,
that's pretty clever.
Way better than we started out with like a comb and a plate.
Yeah, I played with that too. That's the Susskind patent called wavy capacitor. You've seen that. It's horrible. Yeah, right. The forces are incredibly small.
Yeah, they're very, very small. That's what Ivo did. They just jumped our patent and built one of those silly things. But we went a couple of years down the road, and figured out how to do it with flat plates where you can stack them up, you know, a lot.
Yeah. Well, guys, if it's okay, let me
I'm done.
Oh, okay. Drew, thank you so much. Thank you so much. Let me see. We have Bernie and we have Mike. Let me go to Mike real quick because I think he has a very quick update. He wanted to show us a circuit. So Mike, you had a circuit you wanted to show us. Let me bring that in there.
Hey guys.
Yeah, yeah. If you could do that and make sure to keep the sound off. That way we don't violate anybody copyrights.
Okay. It's all royalty-free audio in it, but it sounds all. So this is a energy circuit based off the Bedini SG. Can you guys hear me good?
Yeah.
So, can you see the mouse? My mouse?
Yeah, yeah. So you got a reverse flyback generator. It's a circuit simulator.
And okay, you see the switch here?
Yeah.
And the switch here?
Mm-hmm.
And these two switches?
Yeah.
So this is the positive line and the negative line from the source. And when these two switches close, they'll charge up this coil. And then they'll open. And the flyback from this coil will go out to this direction, onto the opposite source. And this side of the circuit is will feed the other coil up here when the other two switches close. So I had to add two switches because without the second switch, the flyback would feed the opposing coil and you would get pulses on both coils. With just one source plugged into the circuit, I tested it and I would run it and both coils were getting pulsed. So I added these other two switches and to eliminate that. So it's basically
Okay.
4 transistors.
I think
Now they
Jeremiah might
open
have some.
together.
And Jeremiah, you know about Bedini, right?
Let's see where
Yeah, I've taken a look at this circuit and many others. This is a very close proximity to the Tesla switch. And the idea is to bounce back and forth power between two sides of the supply. And what's not shown in this schematic, but what should be shown, is the inductive pathways, where you're looking at there, you just see these tiny little L1 and L2, right? They're barely visible. They look like resistors in the center there, but that's the inductance of the pathway between the two sides of the bank. And so that's what's effectively supposed to be doing the work on the Aether.
See how they're closing and opening?
All right, so when those inductors have a magnetic flux around them, the idea is that the flux expands out into the local space slowly, it builds up slowly, and then it's released very quickly, and so it just dumps, but all that spatial polarization has a sudden collapse that's much faster in terms of amps per meter than the original charge-up period. So because of that, the net amount of ambient energy that might happen to be in that magnetic flux that's collapsing is potentially recaptured in that event. But again,
watch how the two
I've
switches close together and open together.
and most of them just don't work at all. So it's a very not yet verified phenomenon, in my opinion.
Yeah, and that was kind of what I was wondering about. So Bedini is kind of on our question mark list.
I mean, I've got a Bedini 10 coiler sitting in the other room, and I mean, even the schematics, they came wrong. I'm pretty sure that was on purpose, you know. So somebody did get it working. It wasn't certainly because he gave them everything they needed, but you had to at least have an electronics background to fix his schematics before you could even wire the thing up. And that's one of the things I noticed. So I've got like the actual expensive Bedini stuff that was gifted to me by somebody else that bought it way back when Bedini was still alive and building it. But my opinions on that are still, I can tell you for sure.
So you can see the two switches closing together there. Pay attention. The two left ones there.
Yeah, we know how it works. Like,
they're supposed to close and open together. And the other two are not closed when the other two are closed for this to work. And most people with this circuit, they set it up with 2 batteries, and they test it out, and it works. You dump the power from one battery to the other, and the wheel spins the whole time. Well, this circuit eliminates the need to swap the batteries every time one battery empties into the other. You have to swap them because they get, one battery's emptying into the other. With this circuit, it's basically bouncing back and forth each pulse. So there's no need to swap the batteries. So paying close attention to the two switches on the bottom and the two switches on the top, they're switching separately. So the two switches on the bottom are triggered at the base simultaneously, and the other two are on a different trigger, and they're also triggered together.
Okay.
You see how they're switching now?
Relays for this. Most people just use relays, like single, like double pole, double throw.
There's a switch on the positive and the negative here. So
yeah, I know. We can see there's 4 switches in total that have to operate.
Basically, there's a switch on the positive and the negative.
Yep, it's
because you have to disconnect the negative and the positive from one source for it to fly back into the other source.
Yeah. Well, Mike, thank you for sharing this, man. Thank you for sharing this.
It's a little tricky, but it's a switching thing,
Yeah. That's awesome, man. Thank you for sharing this with us. Let me, if it's okay, I want to take this off and I want to go to Bernie now, and then I want to try and go to Dawn after that. Okay.
Thank you.
And Bernie. Oops. Oh,
thanks, guys.
Oh, no, that's my fault. Sorry. Okay.
Both doing it at the same time, but that's okay.
Oh, that's cool. That is cool.
This is I'm going to show first a few different pictures of the self-organization of monoatomics. This is a silver 1 ounce coin anode, and then a copper triple solenoid, what Keshi calls his Magrav coil cathode. And every time I would add more water into the electrolysis solution and disturb the monoatomic materials at the bottom, it would self-organize into these different spirals and vortexes. This one being copper, I believe Keshi calls it CH3. I am not actually sure what the mixtures are, but the material that this orange-brown stuff was made of was pure copper anode and pure copper cathode, and it was turned into this material. But once again, you can see the spiraling within it, the self-organization. Here we have copper oxide and pure white monoatomic copper. This is copper coil anodes, copper coil cathode, and the white being monoatomic, the blue most likely diatomic copper oxide. Here again in that same solution, also forming the spiral self-organization in this area, but a second one forming over here, and it's reversed the direction of the spiral. In this sealed jar, this is all copper, but underneath it you can see pinkish layers, and it's actual copper crystal growing out of it. And it's Sir Isaac Newton alchemy writings that he states this pink crystalline state of metals is when they're able to be transmutated from one element into another. Also at the bottom, you can see this yellow state of Ormus monoatomics, or whatever single atom stuff that's made from copper, and what the alchemists and Sir Isaac Newton calls the yellow sulfuric state. Again, I don't have a mass spectrometer, so I'm not sure if that's the actual composition of this, but if it is, that alone would prove transmutation of elements, as where did that sulfur come from if it is actually copper sulfide that forms. In this jar, I found when you seal these metals in this pink crystalline state, but in the yellow sulfuric state, and then when I opened the jar, breaking the seal, left undisturbed, the jar was actually, it formed all these different almost spirally, but kind of waves, moving waves all around. And it was active for about 3 days. I'm going to have to find the video of that to show it another time. Here again, you can see some spiraling in a cup of the copper oxide. Here is a triple copper coil anode, and you can see that half of it is blue, the other half red pink, as well as going into the white state. But that what causes half of it to be turning into a red state while simultaneously half into a blue, and this red-blue dynamic always being shown and also seeming to be formed in nature. And on some of my other coils that I've made that are more of the bagel coil style of Bob Greenier, I found on each individual wrap, on one side it would be red, the other side it would be blue. Quite fascinating. Here again, just pure copper sealed in that pink red active state. And this cloud right here halfway up the jar, that's actually floating copper, or suspended, I should say, copper oxide, most likely, as it's blue, and it will just stay in this exclude or form these different exclusion zones on the top half and usually the bottom half, and then a divider in the middle, this fourth state of water that Gerald Pollack talks about so much, and that it's quite often forms in these electrolysis reactions. Here, these white tubes that you see, those are actually self-organized, created nanotube structures of the monoatomic copper that forms off the anode sides, and they're straight hollow tubes that just grow and flow, and it's quite fascinating stuff when you see it, and how it just self-organizes and grows in very, very short periods of time with just a very small amount of voltage going in. Most of these experiments are either 5-volt AC or 3.5-volt DC going in. In this one, there's no electricity at all going in, just 2 copper wires connecting a gold chain on one side and a silver 1-ounce coin on the other, with the 2 copper wires creating 2 connections to them. You're creating a small differential, and you can see here off the gold, the white monoatomic gold forming this band here, going and connecting through. It's about 2 inches below the water and line of the top, and flows and connects directly to the silver from the gold. This I just had to throw in and bring up the discussion in APEC, especially the community here. So much debate and bad science on the climate change debate of whether it's man-made and how much we actually impact it. And I don't ever hear or see anyone bringing up the facts of Mars's ice caps as well as the moon's ice caps that seem to have disappeared over the last couple of decades, as well as Mars now having active volcanic activity on it. I believe this no, this was just an old picture with the ice caps.
Nibiru, and it started. It follows.
Well, or just the galactic plane that they say we're now crossing.
There's another star rotating around our star in 2012. It's been documented. It's called Nemesis. It's called Kachina.
Yes, the Nemesis Planet X debate.
Yeah, I'm not going to debate it. I saw the damn thing in 2000. Okay, it's real. And, I thought it was a UFO mothership, but It's not. It's a star. And you
Yeah.
can look up two suns on YouTube and see videos of it everywhere. People have captured it. It pops out from behind our sun. It's not always visible.
I find
And
it a
it's there.
fascinating subject.
And that's
but-
why they chemtrail, to hide it, make clouds. Because there can only be one God, not two suns, not two gods.
Right, but that Mike will have to do an episode all on its own. As
Yeah.
for electrolysis here, once again showing these exclusion zones, the bottom half of this jar forming white monoatomic tungsten. This is a tungsten ring, copper wrapped around tungsten ring, and then the cathode or the anode, sorry, was also a tungsten rod, welding rod that I was using. So this is tungsten cathode or pure tungsten anode on tungsten and copper cathode, and you see the cathode obviously bubbling up all of the atomic hydrogen here, and the bottom half forming this layer of the monoatomics forming, or the armis, and then this clear zone where the ring is of this exclusion zone separating the two layers. This being a pure triple copper cathode here bubbling up the hydrogen, and the pure copper anode, which was a triple copper coil going down, but the green and black nanotubes that have grown off of it, and then these bubbles that start coating. And this I bring up specifically as an idea for Brian Kelly's adding hydrogen through electrolysis to the graphene aspect, is that I find in these electrolysis reactions, when the anode has eroded down and created these nanotubes and grounded itself with the base level, it then spreads its monoatomic layer across the entire base, at which point it then starts growing these bubbles, which they're no longer affected by buoyancy. Instead of floating up, they just stick and layer the anode to the point, I'm going to have to skip ahead here to where they're completely covered. And here is a triple solenoid, I guess more like a spring than a coil. To give reference, here is what they look like before going into the electrolysis reaction. Essentially this right here. And the black part is nano-coated. The normal copper outside third layer, regular copper not nano-coated, but that is what you are looking at here as an anode, only completely covered and stuck with these bubbles, either hydrogen or oxygen, and they don't flow up, they just stay encased on the anode. And here's another one, another reaction demonstrating this full layering of these bubbles on the anode side, and that this, when it was finished, the reaction was finally finished, and I took the anode out, it was pure black coating that was encased on it afterwards, after it had been eroding or corroding into the blue. Here is one of the windings of the bagel coil style of Bob Greenyer's Martin Fleischmann Memorial Project style. This I had come up with and done on my own over 9 or 10 years ago now. Just synchronicity of how things work. Here's a triple maggrav coil that was on the anode side, corroding, breaking down into the blue oxidized layers. And and this yellow. So here it's showing a bit of the yellow when the reactions go full reaction of the yellow, the sulfur state. Sorry, I'm trying to flip through and find a good example of it. I don't have it in here, but it literally goes almost neon yellow. And the alchemist said it's when the metal dies, it goes into this yellow sulfur state. And I've found that when the anode corrodes and you have a double negative going into the electrolysis reaction, that is when it will turn into this yellow sulfuric state. And simultaneously, every piece of, whether it's copper, silver, gold, zinc, whether it was white, orange, or blue, when it turns this yellow sulfuric reaction, when you disconnect the positive in and have double negative still connected, the entire solution, everything within the electrolysis reaction instantly turns yellow. Quite fascinating. And then in this demonstration, I have a copper anode coating. It's eroding into the white monoatomic nano layers, and then also some of the blue copper oxide. And then it hits the middle, this mid point, this exclusion zone area, and suddenly turns into the orange brownish CH3, I believe, or copper hydroxide, as Keshi claims. Or I once again need access to a mass spectrometer to start testing these different metal compounds that are forming and verifying what they actually are, and if the ancient alchemists actually knew what they were talking about, and real transmutations happening in these reactions. This connection here I have is for saltwater jar solutions with zinc strips connecting the jars, and then copper connecting some of them as well, forming all sorts of weird different reactions. But the main point of this and significance is that it's only 5 volts going into it, and there's a huge amounts of hydrogen being formed in all of these jars and reactions here, and quite feasible for just creating hydrogen fuel, usable hydrogen fuel on site before you inject it into the combustion reaction, not having to have pressurized pre-created hydrogen, where this seems, if you have the right amount of surface area and electromagnetic field through these coils, you'll get sustainable low energy reaction that could be what Stanley Myers had going on. In this reaction, electrolysis reaction, you have a horseshoe, or not quite horseshoe, but magnet down there. But this line in the middle that you see is actually an exclusion zone separating 2 halves of this reaction, and that I have a giant LED light on the opposite side shining through, and that it was actually parted. There was a physical partition exclusion zone of pure water down this entire jar between the 2 areas. It was quite fascinating, and it seems that it was the magnet that triggered that. Here's the original cloud of monoatomic or diatomic silver coming off of the anode there that then formed into that. Here's another reaction showing the yellow sulfur state as it got affected there, different coils. And this I bring up, I'll finish with this here for all of you out there with the theory of everything and numbers and dimensions. That's quite fascinating. You actually have, well, the same number of angles in each number when made like this. There's a lot more to dimensional geometry than what in mathematics, basically, is what I'm getting with. And one last spiral of self-organization of this was monoatomic silver. I left out overnight in front of on a full moon, and in the morning it had formed this layer on top and this shiny reflective spiral. Yeah.
Bernie, that's awesome. That is awesome. Thank you. Thank you for that in-depth, man. That's in-depth. You've had a lot going on there. A lot going on. Thank you, sir. Thank you very much.
Welcome. Thank you for giving the time.
Yeah, absolutely. Well, so
I guess, sorry, lastly, here is some transparent aluminum. It's, as it dries out, it's reflecting a little bit white, but it's still actually very, very clear. And this has now been drying out for 3 or 4 months out of water, and it's still quite gel-like. And there you can see that it is actually clear, clear aluminum there, jelly-like stuff. And
awesome.
Yeah.
Well, yeah, Bernie, thank you again. Let me go, if it's okay, because he's been waiting backstage for a while. I want to go to Dawn now, if that's okay. And so let me. Okay, I'm going to bring Dawn in here. Mr. Tadaya, thank you.
How's it going, guys?
Full house today. Hey,
I know.
Do you want to try and share the UAP centralization program?
Oh, absolutely.
And I want to preface this story. Thank you. It's been a long time since you were on. When Jack Sarfatti, he kind of gave me last minute notes. He said I wasn't able to make it. I was like, you know what? Dawn hasn't done anything in a while. I want to see if he would come on. So thank you very much. I'm sorry about the wait. It's been actually incredibly busy, but in a good way. So
no, I can tell. I know you've been cranking out those videos, so I'm almost caught up with them. But yeah, you're doing a lot too, Tim. Thanks for getting everybody together here.
Oh yeah, well, there's so much happening, and it's all amazing stuff. You know, today, I mean, it's just like people are just showing one thing after another. There's so much being developed.
Well, mine is a little bit a different discipline than what you guys are talking about. But we are.
Yeah. Do you want to hit the? Let me see. If you do the present button.
Okay.
And then you should be able to share screen.
Share screen. Hold on.
Yeah, and it'll let you show a tab with the UAP centralization program in it if you have that up.
Do you see it?
And let me add that in there. There we go.
Yeah. Okay.
Yep.
So the UACP stands for I actually have an initial project, but what I'm going to show you guys just briefly is defining the veracity variables, which is how credible a UAP report or a UFO report would be. I wanted to show you guys first the UACP, which stands for the UAP Analytic Centralization Program. It is something that we're working to try to get together in getting a lot of different disciplines and different data sets, so that way we can put everything into one analytic centralized hub. But what I did was I gathered New Fork data here. So we have, for instance, the city in Nevada, Henderson, in USA, of course. The shape that they saw was fireball. They saw it for 20 seconds, and the comments were very strange object sphere over Henderson, Nevada. The date that it was posted was in May 8th. And I have the latitude, longitude. I have how long the comment was and the year, date, and so on and so forth. So this is just like the raw data, but I don't want to try to drown too much with the data sets, but I wanted to show you guys how that typically looked like. For instance, here's one in Florida saying my wife stepped outside to get some laundry and she noticed a bright orange light hovering in the sky and called me out to see. Just a bunch of different comments, right? There doesn't seem to be any structure to how these comments are ranked, but that's just because we're looking at a base New Fork data set, the National UFO Reporting data set. But what I did was I got together with the Scientific Coalition for UAP Studies, SCU, and they've already started, they've been wanting to apply the natural language processing toolkit, which is provided by Python. They've been talking about natural language processing against UFO type reports and firsthand sightings and that type of data set. And they wanted to use a lexicon that would help identify more scientific focus or more scientific comments and report descriptions versus the more emotional more emotional comments that were reported. And the way they did that was they associated words with ratings. So for instance, if someone said the word above in their comment, that word would be counted as 2.0. If they used AF, probably standing for Air Force, that would be rated as 3. Air Force is rated as 3.0. Witnesses is 3.0. But if you use word like Zoom or zoomed, it would count as a -2. So that's kind of the lexicon. And there's 349 non-zero rating lexicon words here that they use, that SCU used in order to hand jam natural language processing on, it was like maybe several thousands of reports. So they had their own algorithm. But what I wanted to do was I wanted to attach a natural language processing toolkit, which is called NLTK. That's an open source software package by Python. I wanted to embed the SCU lexicon into that natural language processing toolkit. And let me just show you guys really quick. I don't want to show you guys too much code, but what I did was I took the lexicon and I added the lexicon words into a natural language processing protocol that would help us identify the more scientific comments versus the more emotional ones. So this is, first of all, for instance, this is an example of how the SCU lexicon was used to identify higher rating comments using the SCU lexicon only. The word perfect came out as a rating of 6.0. So when it identifies a comment that says this, for instance, 4 bright orange lights in a perfect square that was slowly drifting before separating and disappearing, that was found in Memphis, Tennessee on March 4th, 2008. That gets rated as a high according to the SCU lexicon. Again, that's without applying natural language processing toolkit. Another word that came out as high is 3.0 for the word west. And again, that comment would be something like the crown object and balls slowly come out of the west and move to the northeast. Again, the next word is day, which rated 3.0. We were under brilliant illumination that was much brighter than the 2:30 p.m. afternoon clear day sunlight. So it identifies those kinds of reports or comments, and it ranks them according to the SCU lexicon. But what I decided to do was I took a Vader sentiment analyzer. And the Vader sentiment analyzer is basically attuned. It's what it is. It stands for Valence Aware Dictionary and Sentiment Reasoner. It's a lexicon and rule-based sentiment analysis tool that's specifically more attuned to social media comments. Like, I think they did a problem set on tweets and identifying which words were negative emotionally and sentimentally versus what were more positive. But I took those words out, what made a positive, negative sentiment, I took them out, and I replaced them with only the scientific values that I got from the SCU lexicon dictionary. For instance, the word northeastern, if that would be identified if that was found in a comment, it would be ranked as more positive versus a comment that mentioned the word shocked or skin or star-like. If the word star-like or storm shows up in a comment or in a report, it would rate that less. So what I basically did was I took the NLTK, which is a pre-built Python toolkit. I embedded the SU lexicon in it to identify not the positive and negative sentiments, but the more scientific versus the emotional sentiments. So the more positive it is, the more scientific it is, using words like approximate, appearance, degrees, clockwise, momentarily, locomotion, witnesses. If they talk about multiple witnesses, that gets ranked a little bit higher. Rectangular or upward, telescope are positive words. But we also have lesser positive words like location, triangular, hover. These are lesser words. So I basically just embedded that. And because of that, let me scroll all the way down. I was able to get not just the lexicon word that it uses and the rating that it got because of the word north. This comment, for instance, got a rating of 3.0. But now I get a veracity score, 339, for instance. This is just an arbitrary scale, right? But what I did was, in order to get the veracity, I would take the scoring, the natural language processing scoring. I would get the compound of that. So for instance, in this case, the compound is 0.838. That means that it's 83% in the positive score, which means, because of the lexicon that I applied, identifying more positive to be scientific versus the negative or lesser values to be more emotional, 0.838 or 83%, it's coming out to be 83% more scientific than it is emotional. And that comment would be something like this: in the northeast sky, a huge green meteor-like event with a brilliant bronze-like tail and sudden instant after seeing the green fire. A huge high altitude brightly lit fireball with a brightly lit trail which ended in a huge explosion disintegration seen in the southern sky. That was ranked high. That was ranked at a 3.0 according to SCU lexicon because of the word southern. We have one right here that uses the word appear. I was watching the sky like I always do on a clear night, because you can always see what appeared to be stars riding along the night sky. That obviously keeps going. These comments are only showing the first half, but I'm going to show you guys some longer ones here in just a second. So I get a ranking here, and I'll try to highlight that here. The veracity ranking at the top here that we see, or on towards the right of the screen, 339, and then it decreases. So as I go down, the descriptions are a little less credible according to the lexicon that I'm currently using right now. I'm totally open to suggestions on the approach that I have for this, but currently this is what we have in regards to using natural language processing. So what I did was I graphed out those reports on a multidimensional chart here. So although it looks like it's a 3-dimension chart, because we have the Powell compound score, the veracity, and then the date posted as you go further down the graph, the size of these bubbles actually represent the size of that comment. So that's one more dimension. And then the color of the bubbles represent the rating, the Powell score, the SCU rating. So for instance, this guy at the bottom, the size of the object, and its perfect detail left us with no doubt of what we were seeing. That gets ranked higher because of the word perfect, for instance. So that's one little application. Here's another 3D graph. I won't get into that, but the coloring, this is also a 5-dimensional graph because we have rating, the score, the date posted, and then the veracity. So the higher veracity ones come out to be more yellow than they are purple. But what I did was, instead of new fork data, which were kind of spread out, I took MUFON data and MUFON reports, and I applied exactly the same lexicon. And because of that, I was able to get these really detailed reports here that showed up. So really quick, just the basic idea of what the MUFON data set looked like. Some of them were coming out with no detailed descriptions at all when you look at the data set normally. But as soon as I applied the lexicon and the natural language processing toolkit, and I ranked them by their veracity, which is the very, very last, column here to the right. These ones are coming out to be, for instance, like 1,355 in regards to veracity. The Powell positives, the Powell negative came out to be 2.3%, and it came out to be 10%, 10.6% positive. But I'm not going to read this, obviously. But this is a very detailed description of what someone was seeing in the sky. And I have the lat longs for it, the location for it, a very detailed description of what they saw, when they saw it, and again, the data set goes down. But what this did for me was it helped me identify the word credible is a tough word to use right now, but I'm currently collaborating with SCU board so that way we can better fine-tune these algorithms that I'm using to find the more credible reports. But currently, the ones that I've pulled out so far, the ones that are ranking to be the highest veracity, have been rather compelling. And I'll attach the link to the chat, to the comments here to this. But you can go on my CAG, you can go into my website, dascient.com, and this shows up. And what I did was basically I took all of these reports that are showing up in California or all throughout the United States, and I would rank them all to show which reports are more credible.
And Don, I'm going to drop a link into the Dascient website right now.
Yep. So if you go to the Dascient website, you can see a lot of the work that I'm doing. It's the second link under analytics for the natural language processing application.
Yeah,
here.
this is a remarkable amount of work that you've done. People should recognize that. And so what you're doing, again, you're going through UAP reports, you're categorizing, you're breaking them down, you're doing very intense data analysis and scrubbing. And I think that this is so valuable because there are literally several lifetimes worth of data in terms of reports that are out there. The problem, and this is something that you found when you got into it, and most people aren't aware of this, but the reports are not filed consistently. So it makes it really difficult to break them down. You've got different people taking reports, different people putting data in, different people doing it different ways. And so I know one of the surprises that you had when you got into it was it's like, okay, this isn't consistent data. I can't just run, so.
We're looking at 66,000 new fork reports, and that's watered down from the original 80,000 new fork reports. I watered it down to 66,000. And then when it comes to MUFON, which consists of these large descriptions here, this one, for instance, that I have highlighted is written by a lieutenant. He has a background as a criminal investigator, claiming that they have seen a UAP and talking about it in great detail. This MUFON data set consisted of 29,000 rows of reports. And the fact that I was able to run the natural language processing algorithm against the 29,000, or actually took 3 hours to run on a sample of 1,000. So just to give you a perspective, I did let my computer run to work on the entire 30,000, and it took about 6 to 7 hours to do that. But for the sake of computational efficiency, I just did it on a sample of 1,000, and I was still able to get some rather compelling reports. So again, computation is an issue here, but it does give us more credible ones. It does give some insight on the type of reports that are being submitted here. And yeah, it is historical, because, for instance, the one that we're looking at here is dated back to 2009. We have MUFON data going all the way back to 1998. And then I wrap up the notebook with some data science machine learning algorithm here that's actually able to take the MUFON data. So the MUFON data has a variable that's called disposition. Like for here, you're seeing IFO. That means that it's been an identified flying object. And then the other ones that are just like rated unknown. That's a part of the MUFON data. What I was able to do at the very bottom doesn't have much to do with natural language processing, but what it does is actually it's able to predict properly with a 60% accuracy, for instance, whether or not that disposition value was predicted properly. So in this case, the disposition of that particular report that I did as a sample test case was unknown. I wrote a machine learning algorithm here that's able to predict that variable, and it predicted it properly. So that's just an example of what I'm currently working on. So if anybody has insights or wisdom or any idea at all as to how we can better identify more credible reports using natural language processing, I'm totally open to those suggestions.
Yeah, and again, so Dascient.com, I dropped the link in. I'll drop that link in chat one more time. Don, thank you. Thank you so much for coming on and presenting this. Again,
I wish I could show you guys my larger page, but this is actually not just USA data. The 30,000 reports that I have is from all over the world. We do have some ethical data wranglers on our team, right, Tim? So we have access to worldwide data from Brazil to European, including even Asian reports are showing up as being pretty credible. And another benefit to using NLTK by Python, natural language processing, is that you're able to run it on multiple languages, not just English. So if I'm able to update the SCU lexicon, for instance, to include multiple languages, I'm able to identify the more scientific versus emotional reports, which is really just going to do a lot of honing in, you know what I mean, on finding credibility.
This is amazing. You're using 21st century technologies to analyze data that has just been collecting dust for decades, and that's it's remarkable. This is only going to lead to amazing results over time. So
oh yeah, I sure do certainly hope so.
Yeah.
Again, I'm still collaborating. I just sent the work over to SCU and I said, hey, go ahead and rank these for me. I gave them a list of all of the reports or a random list. I gave them about 20, and I wanted them to rank it themselves based on their experience. They have over decades of experience of going through these types of reports and identifying which ones are more credible. And I told them to rank it for me. And then I just got that email back with their scores. So I'm about to compare to see how my algorithm did. And I'll update you guys on that whenever
Awesome.
I get a chance to.
Well, thank you so much, Don.
Thanks for letting me showcase this. I really do appreciate that.
No, absolutely. Well, let me take that one out. And you know what? I'm going to bring everybody on stage. We have not been clapping. So we have John Brandenburg up next, but everybody, a big hand for Don, as well as for everyone who has given lab updates, for Bernie, for Jared, for Mark, and for Jeremiah, and all of you guys. You guys are all rock stars. You're all doing independent things, going in different directions, but
I better learn how to play a guitar.
There you go.
Tim,
John,
you're the
air
glue that
guitar.
brings us together. You
We
are
should
the
do
glue.
we should do a talent show APEC open mic one of these days. A
I
real
think this
open
is
mic.
this is our talent show.
You just gotta play
I'm-
the strings of the aether.
I'm
Play
just
them
I'm the only-
real hard.
play the violin.
Yeah, I'm the only one here with no talent. So
Oh, I'm the sphere of harmonics. And Tim, that's not true. Your talent is bringing us all together and asking the right questions and showcasing everyone's work.
oh, thank you, Bernie.
Yes.
Yeah, I mean, you guys are the ones doing the work. So, but yeah, if it's okay, let's go to Mr. John Brandenburg now. I'm going to put him on solo layout. And John, I also, let me see, I'm going to add the PowerPoint in there. And what I'll do is remove everybody else. And that way it's just you. And so I guess I should mention that, again, when Jack indicated that he wasn't able to come, I reached out to Dawn and I reached out to John. And for both of them, I said, you know, oops, I said, can you guys come on in and present for us? And so there we go. Perfect. So John, thank you, sir. I absolutely appreciate it. Again, you guys are saving my bacon. I was excited to have Jack on. It is not his fault. He just got pinched by his schedule, but I'm so happy that you're able to come on. Why don't I do this? You can just say forward or just say next slide as usual, and just let me know.
Okay, can you hear me okay?
Yeah, no, you sound great. You look great.
Oh, okay, great. And I hope everybody else can hear me. Yeah, Tim, you're doing a great thing here, and I want to support you. And I was looking forward very much to seeing Jack's presentation. And so, you know, Jack's a really smart guy. We should always listen to him. And
Yeah.
So anyway, Jack's research follows parallels to mine. You know, he's convinced that we're not alone in the universe, and that not everybody else in the universe is is nice, just like on Earth, just like our own neighborhood. And then he's also you know, a believer that we can modify gravity fields with strong E&M fields. And you know, that's these things are both very important points. And so anyway, so I'll look forward to seeing Jack's presentation some other time. In the meantime,
yeah, and just let me know.
Let's see, you say I'm a rock star, I'll do an air guitar here.
There you go.
Intro.
I'm gonna, John, I'm gonna hide myself.
What?
And just I'm gonna hide myself. I'm still here. I'll do the next slide. Just let me know when to do next. And
there are two ways I can take that, Tim.
No, I don't mean it like that. I mean that way people can focus on you.
I'm about to get talking here. Okay. Anyway, I wanted to present to all of you some work I'm doing. I'm a plasma physicist. I'm not a quantum theorist, and unfortunately, a lot of the mainstream of field unification efforts is in the quantum realm. And the first thing you run into when you enter the quantum realm of relativistic, quantum mechanics, which is a jumping point to getting a relativistic, general relativity, a quantum version of general relativity, quantum gravity, which is everybody's goal now, is you run into these things called spinors. And I mean, the community is evolving. Remember, quantum mechanics began as a very kind of non-intuitive, abstract, mathematically abstract field. And that kind of persisted for a long time. And one of the things that emerged from the Dirac work of Dirac, the Dirac wave equation, which predicted antimatter, is that like electrons are they're best represented in the quantum mechanical realm as a thing called a spinner. And then you ask, what's a spinner? And it's almost as if they invoke, oh, well, only the third stage Masons in this field can understand what a spinner is. It's so profound, you know. And then they'll say it's a Clifford algebra or something like this. This is what has been told to me. And they, you know, the strange effect of revolving things through not just one revolution, but you have to revolve them into two revolutions to get back to your starting point. These are big obstacles to our comprehension. And what we want is comprehension. We want everybody, even kids in high school, to know what a spinner is and think about them so that then they can go on into college and then grad school and become astrophysicists or field theorists and solve the great problems that are confronting us. We're going to have to become real quick learners. If we're waking up to the fact we're not alone in the universe, and my own research indicates, and all the reports are consistent with that. My own research on Mars, and it's and also the results of the analysis of Avi Loeb's debris. We may live in a rough neighborhood. As Obi-Wan Kenobi said, you know, we have to go into this this bar at Mos Eisley Cantina. Remember that bar scene? And he says, but watch your step. This place could get a bit rough. So we have to become quick learners and move ahead. And part of what we need to confront is a conceptual roadblock that people have about spinners, because spinners are very important. So I have been banging my head on this for the last basically 2 months. Actually, I started in grad school when I started studying the Dirac equation as you know, in quantum mechanics. But so let us enter into this Mos Eisley Spaceport Cantina, and the first thing we confront is the doorman, who is a spinner. So the title of my talk is The Nuts and Bolts of Spinners. You'll see that that's actually a pun, but I want this to be a physics-based discussion. We're going to try and talk physics that you can demonstrate on a tabletop in front of you to understand what a spinner is and its reality and its importance in the cosmos. Next. Okay, overview. First, we're going to talk about what is a spinner. I'm going to tell you. We're going to talk about the physical reality of spinners, literally nuts and bolts, the vector mathematics of spinners, and I'm going to just pass over this lightly. I'm just going to use very basic vector analysis, some physical demonstrations of spinners, and what is its physical meaning of the importance of spinners. Why are they important, and what does that mean about the universe? And then I will summarize. Very good. What is a spinner? We're confronting the doorman in the Mos Eisley Spaceport. Next, please. A spinner is defined, and this was the best definition I could find on the web. It was from Oxford. A spinner is a flagpole with a flag on it. Okay, let's analyze this statement. And you know, I dug into the mathematical physics of what he was talking of this, what this guy was talking about. I can I'll post a link later to Tim so that he can, everyone can go look at this discussion at Oxford. A spinner is a flagpole with a flag on it. Okay, the flagpole gives you a vector. We call that a polar vector, by the way. It's just a direction and a length, a magnitude. What's the flag? Well, the flag marks the rotation around, which is what's called a different variety of vector in vector analysis, called an axial vector, also called a pseudo vector, but it is actually an honest to God vector. An axial vector around the axis of the flagpole. So we have a flagpole sticking up here, and then we have a rotation around its axis. You could also call that a quaternion. Vectors come, these are used to analyze baffling things like gyroscope motion. Now, vectors come in two types. Ordinary, kind of run-of-the-mill vectors are called polar vectors. That's like a velocity, a momenta, an electric field is a polar vector. That's how it's represented physically, in mathematical physics. And then you have axial, or what is called pseudo vector, but that's a misnomer. And that's, instead of just having your finger sticking out here, that's a vector. This is a axial vector. My thumb is an axial vector. What you really have to pay attention to is my fingers. My fingers go around. Here's this right-hand rule. And the axial vector direction is determined by a rotation direction on the right hand. And by the way, there's some evidence from weak field theory and decays of certain things that God is in fact right-handed, and he actually favors the right side. That's one of the reasons we have matter in the universe rather than antimatter. But that's an aside. Let's not worry about that right now. We have regular vectors, and then we have a spin or a rotation vector indicated with a direction indicated by my thumb as my fingers curl around. And if we have a vector that's parallel to the thumb, then we have something very interesting. We have combined an axial vector. Well, we've combined a polar vector, a direction and a magnitude, with a parallel axial vector. Now, what is a spinner? A spinner, as near as I can make out as a mathematical physicist, is a polar vector combined with a parallel axial vector. And you'll see what I mean, and you'll see why they're important. A vector is a flying musket ball. A spinner is a flying rifle bullet. It's spinning along its path of travel. That means the spin vector and the momentum vector are aligned. That's a spinner. And next thing. So now I've told you what a spinner is. Here's some examples. A dust devil, or when you get a brush fire, you get a fire whirl. You get a violent updraft of hot air due to the flame, and it spins. It's a vortex. So it's very stable, very persistent, very coherent. You have a submarine propeller. The nose of the submarine, you could say, well, that's a vector. The tail end that makes the submarine move, that's a propeller shaft that's spinning with a propeller on it, that's a spin vector aligned with a direction vector. That's a spinner. So the nose of the submarine, that's just a vector, a normal vector off the nose. The back of the submarine, the thing that makes it move, is a spinner. And of course, we have the example of a tropical cyclone. I'm just amazed at how much it looks like a galaxy. In a tropical cyclone, you have a big updraft of warm, moist air that then gets caught with the Coriolis force, so it develops a vorticity, and they say, oh, it gets very organized. The more organized it gets, the more coherent it gets, the more it becomes a real spinner, honest to God, the more violent it is. The worst hurricanes that hit people are beautiful. Just like the universe, the whole universe itself. It's not only beautiful, but occasionally a dangerous place. You haven't lived next to a gamma ray burster. If we had, we wouldn't be having this conference today. So these are examples of spinners, not only in nature, but in technology. Next. Okay, here's just some other examples. A nail is a vector. A wood screw is a spinner. A column of smoke rising from a fire on a still day rises straight up. That's a vector field. That's a ordinary vector field. That's just an updraft of hot air rising from the fire, carrying smoke with it to make it visible. Okay, smoke column. That's a vector. That's just an ordinary vector field, or what you call a polar vector, rising in the gravity field. A tornado. That's a spinner. You want to know the difference in nature between a vector and a spinner? Go through a tornado. Watch somebody, watch some smoke coming out of a chimney far away, and then watch a tornado come and tear the chimney apart. So, my friends, spinners are all around us. We just did not recognize them. And just like the tornado, just like a wood screw, just like a dust devil, hurricane, if we take a structureless medium, air, water, and we impose a structure on it in terms of a vector field, the things that persist, the things that are robust, the things that are powerful are spinners, not vectors. Sure, occasionally a tidal wave will come in. Okay. The surge of water, that's a vector. But it's when the wave breaks and forms a vortex coming in, rolling on you, that's a spinner. So spinners are important because nature loves them. And large-scale persistent structures in nature, structures that emerge out of things that were formerly structureless, just a bunch of air and clouds, suddenly wraps itself around into this coherent tornado and barely tears you another asshole. That's a spinner. So, friends, I've initiated you into the third level of the Masonic Lodge of theoretical physics. Congratulate yourselves. They're big. Well, these guys are used to doing really abstract math. So people ask them, well, what does this really mean? and it's it's particle wave duality, it's Schrodinger's cat, something like that. No, it's a smoke column versus a tornado. It's a tornado. An electron is somehow a tornado, an electromagnetic tornado. That's why it persists. That's why it's stable. That's why it's coherent. It's because it's a spinner. If it was just a smoke column, it would dissipate, the wind would blow, it would lose all of its structure. But in the structureless medium of waves, of quantum mechanics, an organized entity with a vector combined with a spin vector, whenever the electron moves, and remember, the electrons don't all, because of the Heisenberg uncertainty principle, the electrons are always moving. If you get down, if you focus, the deeper you focus on their motion, the faster they move. Finally, they're moving back and forth with the speed of light, and their spin vectors, because the electrons have spin, they have to align themselves along that velocity vector going at the speed of light. Another example of a spinner is circularly polarized light. The light wave is moving, has a pointing vector, and the rotation of the electric and magnetic field vectors that determines this polarization, right or left, chirality, that is an axiovector. So you combine the two, and that means fundamentally a photon, either with spin vector along its light, its path, or against its path, is a spinner. What's interesting, neutrinos, which are involved with the weak force, you can't get, they only have one polarization along their flight. They're spinners that don't exercise their other degree of freedom, where the spin vector could move back across, be against their motion. It's always with their motion. Where a photon, you can have rotational polarization going left, or rotational rotation going according to the right-hand rule along the same path. So photons can have two spinner states, but a neutrino, strangely enough, can only have spin aligned along in a positive direction along its flight. And some Chinese American physicists got the Nobel Prize, and especially the woman in charge of that experimental effort got the Nobel Prize for discovering that that was true. So next, now let's talk about the physical mathematics. And I'm not going to get into abstract math. You never hear you'll hear the, people start banding around, oh, Clifford algebras and SU3, SU2, etc. These are all important, but the physics is actually can be understood through fairly straightforward vector analysis. So here we have a spinner that has, let's say it has two components. It has a polar vector and an axiovector, and they add up to one. It kind of adds up to a unit vector. Okay, there it is at the top of the page. And we just say that the magnitude of the polar vector and the magnitude of the axiovector are both 1/2, so they both add up to 1. Now, if we add a spinner, then what we do, you're standing at your bathroom mirror. You're pointing at your mirror. You're wearing you're at a conference about rotation. So you're wearing a name tag. It says hello. Could interpret it as screw you. But anyway, you look in the mirror. Okay, your finger vector, which is the normal vector, is reversed. It's pointing at you. Right back at you. It's -1. Let's call your finger 1. In the mirror, you're seeing -1. However, the rotation determined by the axial vector determined by your thumb, hold up your thumb, do the Hitchhiker's Guide here. Okay, we'll point it towards myself. Okay, that's a, oh, the camera image is actually reversed. Okay. Yeah, it's reversed. Okay. Yeah. Oh, okay. I can read my name on my hat, Kepler Aerospace. Okay. In the mirror, the hello is reversed. But the rotation vector is technically, if you just look at the badge, the sense of rotation, it's the same. It is unchanged. That's because the mirror reflection is a coordinate transformation that takes only one axis of the XYZ and reverses it. In this case, we'll call it the Z axis. We'll call up and down, Y, and side to side, we'll call that X. So Z is into the mirror, in the coordinate system. Okay, so the thing pointing out of the mirror, that's negative now, a negative vector. But the rotation vector, because the XY, it's determined by the XY orientation, it's not affected. It's pointing in the same direction. Now, let's just say you're a little bit vain. You not only have a mirror, but you have a big computer screen right next to the mirror that's putting out the camera image, just like I'm looking at one now. Okay. In that mirror, the rotation vector is also reversed. It's going clockwise where before it was going, before it was going clockwise, now it's going counterclockwise. The spin vector is reversed. So if you look at the spinner value, it was VA minus VP, which was the polar part. The polar part reverses, it cancels the axial vector, so you have 0 technically for this spinner vector at theta equals pi, which is your mirror reflection. You're rotating the z-axis into the mirror at and you're going a half rotation. So positive x becomes negative x in the mirror. Okay, on this other place, you've not only rotated the z-axis, you've also rotated the x-axis up and down or unaffected. His head is still, his head is still there where it's supposed to be. But his hand is different because that's a camera image. That's what the camera is seeing. That's what other people see. And in that, when you add up, do the bookkeeping on the spinner, you have a negative axial vector. The axial vector has reversed. So is the polar vector. So now it has -2. So you actually rotated the axial vector through pi also. So there is the origin of the half angle formulation. Next, the half angle formula and we can look at this in terms of theta, which is, let's call it the rotation of the z-axis from being 0, positive z with u, and then you rotate it through angle theta, it becomes negative z. Cosine equals -1 at pi. And as it turns out, when you work out the math, you get a half angle formula. So it's cosine squared of the half angle. Now, the polar vector is, let's call it a magnitude VP times K, the Z unit vector. And VA is a combination of the VX and the VY, because they're put together in a cross product. So the axial vector is the result of a cross product in the XY plane, whereas your polar vector is just pure Z. However, the cross product gives you a Z vector also. This is in the more abstract math, the interesting coincidence that in 3 space, you can have a rotation symmetry group SU2, and it overlaps SO3. So you have 3 unit vectors to describe just 3-dimensional space, and the combination of the 3 vectors in cross products gives you another 3 axes that correspond exactly. So it's a 1-to-1 correspondence. That's one of the aspects of our existence. That's reality, friends. You must remember that as physicists, if we call ourselves primarily physicists, we're not concerned with alternative realities. At least not yet. Maybe in the future. But right now, we're concerned with reality. And that description of reality we've evolved during using physics that we understand is primarily phenomenological. We're describing what we see and experience, not what it should be mathematically, but what it is. And this is what it is. People tell me, oh, the mirror reflection, that's not really real. Well, have the power go off completely and your camera image disappears. You still got your mirror image. It still exists. The camera image went away. So if you throw a tennis ball at a wall and it comes back and hits you in the head, that's a reflection, my friend. And that's reality. That's a mirror reflection of a polar vector, of the momentum of that ball. So mirror reflections are reality. They are a reflection of reality. Alice through the looking glass? Yeah, that was a good one. All right, next. Now, we can get into more sophisticated things, and I wanted to show you a lovely video of a lovely Indonesian woman doing a candle dance. This was invented in Sumatra in Indonesia in time immemorial. They noticed they could dance, they could manipulate a plate with a candle on it and keep the plate and the candle constantly vertical, rotate them around below the level of the shoulder, and then raise them above the level of the shoulder and keep turning them in the same direction, and they would come back to where it started. Now, that is an illustration of the 2 pi reversal of things, and because that's where your arm gets all twisted. You can't go, if you try it, hold your right hand palm up or your left hand, whichever you like, and twist it around 2 pi, it's twisted. You can't go any farther as long as you keep it below the level of your shoulder, which is the pivot point. Then raise it. You can keep going. In fact, you untwist your arm. How can you untwist your arm? By twisting in the same direction that it started. Well, because of the math. I'll show you there. Next. Unfortunately, we can't play you this nice video, but it was, anyway, it's called Tari Lilin, Sumatran Candle Dance. Here I've just diagrammed it out. Your hand, as it turns out, is a spinner also, because it's connected to your body. It can't, like a gyroscope, it can't just rotate freely. It's got to rotate according to certain rules. So you start out with a upraised palm. You twist it around 180 degrees. And then you twist it another 180 degrees. Okay. It's now technically 2 pi out, but it's connected to your neck. It's connected to your arm and shoulder. So this is below the level of the shoulder. If you raise it above the level of the shoulder, you can then continue twisting it, turning it, and you get back to the original state of the thing. And what you're doing when you raise it above the shoulder, which is a pivot point, kind of an origin, mathematical origin of the twist vector, it reverses the twist vector. So one thing you're doing is you're twisting your arm, and then you raise it above your shoulder and keep going the same direction, and you've untwisted it. So it's, in a sense, you're not really rotating through 2 pi, you're rotating negative 2 pi back to your original state. The mathematics is the same. So there, I've explained the Tari Lilin Sumatran Candle Dance, for which I am grateful for some lovely Indonesian women showing me this. I'm just kidding, actually. No, they had some nice videos. And anyway, now, so where does this leave us? Next. By the way, I'm going to put this up on my website on ResearchGate so everybody can look at it longer. Okay. Explanation. Raising the plate, just raising it, reverses the rotation sense because the shoulder joint is a pivot point. Everything is connected. The plate cannot rotate independently of the rest of the universe. It's connected to it by your arm. Everything is connected. I say that in my science fiction novel about the collapse of the UFO cover-up. The heroine is constantly muttering to herself, everything is connected. The twist below the shoulder becomes an untwist above. And you can see this with just a nut and bolt. If you take a bolt and its head is facing away from you, and then apply a right-hand torque to the nut on it, it gets tighter, righty-tighty. Okay, flip the bolt around so now the head is facing you, and apply, from your own perspective, another right-hand torque. Continue that. This time the bolt loosens. Lefty-loosey. You've converted righty-tighty into lefty-loosey by reversing the orientation of the bolt. And of course, anyone who's worked on anything that has bolts on the underside knows how frustrating that can be, because you end up turning the nut the wrong way when you want to tighten it, instead you end up loosening it. Finally, it falls off the bolt and you lose it down in the oil, something like that. So anyway, as you can tell, I'm a veteran of many amateur attempts to repair my car in my youth. So we have figured it out, you guys. You're now initiated into third level Masonic Lodge of Physics. You know what a twister is now. Be happy. Celebrate. Watch a video on the Sumatran or Indonesian candle dance. There, they got one on YouTube. So friends, the mystery can disappear. Next. Okay, just as an aside, one of the other things that helps the mathematical description of this is imaginary numbers. You can consider a spinner to be a real vector plus an imaginary vector. Even the term imaginary is perhaps going to have to be revised. Like pseudo vector, it's going to have to be thrown out and attached to something else. However, I did use the line in the novel. The heroine says that she says, the situation is partly real and partly imaginary. Therefore, it is complex, she says. I had fun with this novel. Anyway, Morningstar passed the collapse of the UFO cover-up. So 1 plus I, complex number, you can represent that actually as two matrices. Very simple. One is just the identity matrix. The other is a rotation matrix. And you can very quickly, using the laws of matrix multiplication. Whoops. Whoa, what happened? What happened? Tim. Tim, what happened?
What slide were we on?
Oh, we need to skip back to.
I'm not sure why. There, imaginary and real numbers.
Okay, imaginary real numbers. Okay, look, imaginary number I looks very mysterious, but you can actually break it down into a matrix. Check it yourself. Like I said, I'm going to have this posted on ResearchGate on my website there. Anybody can download it and check it out for themselves. And I'm not afraid to be wrong. But I'm not wrong. I know what a tornado is, and I know what a smoke column is. One is a vector, one is a spinner. Now, to describe spinners, you can use a complex vector. You can use a normal polar vector, and then say an imaginary. What you're doing with the imaginary vector, part of the vector, it's the rotation around. It's the rotation around the polar vector. So you can verify very quickly using the laws of matrix multiplication that this matrix, rotation matrix, actually gives you the properties of I. You end up, if you multiply them together, it doesn't matter which order you multiply them in, you get the identity matrix 1 multiplied by -1. There you go. Next. Okay, now getting a little, and I don't want to be getting into anything truly abstract here, but if you just take unit vectors in 3 directions, I, J, K, represented by those vector matrices on the right, 1, 0, 0, that's the x-axis, 1, 0, 1, 0, that's the y-axis unit vector, and finally z-axis. And let's imagine we have a spinner that points in the z direction. Okay, the we can represent that as a matrix that rotates things in the X and Y plane, but doesn't disturb the Z axis at all. And what it does on the Z axis is it just gives it a magnitude, in this case, 1. So the matrix operation, if you take this spinner as a set of unit vectors multiplied by a matrix, then you can get a spinner. Now, this is a lot more complicated, my friends, than just a vector. In fact, if you can make it simple again if you just reduce the 1 and -1 in the upper left-hand part of this matrix to 0. Then you've just got an identity matrix with one, or a kind of identity matrix, and it maps Z into Z. Simple, simple, easy peasy. That's just a unit vector, polar vector. But when you add the complex part, which is the rotation matrix up there, affecting the X and Y, then you get the rotation, the flag on the flagpole, the spin on the rifle bullet that makes the rifle bullet a spinner and a musket ball just a vector. Next. In summary, spinners can be understood in terms of standard vector analysis. Shocking. Horrifying in some circles. Oh my God. He snuck out of the Masonic Lodge after the third level meeting and is waving signs on the street. He's handing out papers of all our secrets. No, it's not like that at all. It's these guys were trying to do something very, very new and strange, quantum mechanics, and they evolved strange new mathematics to describe it. And quite frankly, it is hard to understand. I remember Feynman, love Feynman. He was asked about general relativity and the two great frontiers of physics back in the 60s, general relativity and quantum mechanics. And he says, well, I think there's about a dozen people on Earth who actually understand general relativity. But he said, but nobody understands quantum mechanics. He had just won the Nobel Prize, by the way, for inventing quantum electrodynamics. And even Einstein was very annoyed with quantum physics. He says God does not play dice with the universe. He told that to Bohr, Niels Bohr, inventor of the hydrogen atom quantum model, and Bohr roared back, "Quit telling God what to do." In my imaginary conversation with Al Einstein, I say, Al, God may not play dice, but he does own a fine casino where dice is played. So my friends, you now know what a spinner is in physical terms. Clifford algebras, all of this other stuff, rotation matrix, that stuff can be studied and understood. But what you basically understand now is what a spinner is, why it is so important. Nature loves spinners, and the human race emulates this love by making things like high-speed propeller shafts that propel nuclear submarines and all sorts of other things that spin as well as move, and they move along their spin axis. So guys, girls, you now understand this. Think about it. And like I said, I'll have this on my ResearchGate website. Anybody can download it and look at it and throw rocks at it. The rocks are vectors.
There we go. John, thank you so much. Okay,
you're
what I'm
welcome.
going to do is I'm going to take that down. I will put the remaining guys. So we are at 4:59. I think after this, we're going to close things down for today.
Sure.
And so, John, Mr. Brandenburg, thank you so much. Thank you so much.
I have taught a lot of physics and engineering and astronomy, and I love it when I understand something well enough that I can explain it to somebody else and they understand it. So it's anyway, Tim, my great thanks for allowing me to share this little bit of mathematical physics.
Oh yeah,
which
absolutely.
is highly important because you can't understand what the quantum people are doing now unless you understand spinors. Unless you understand, at least in a physical sense, what a spinor is.
Yeah. Well, John, let me thank you once again. We are exactly
much.
at 5 o'clock. It is
All right.
a wonderful conference. I'm going to close things down for today. And
okay.
And I will put a copy of this. I'll put a copy of the PowerPoint up as well with the notes.
Good.
And again, thank you so much. I genuinely mean that. What an amazing way to end an amazing conference session.
Dream of spinners tonight. Dream of spinners. Okay.